So welcome to the Land Ice Working Group session, and we're going to have a bunch of amazing talks that are going to be about 15 minutes each, 12 minutes for the talk, and please leave 2 or 3 minutes for questions. This is the 30th anniversary of the CSM workshop, and so because of this, we thought we would have some fun, especially after lunch, where we're all a little bit, heavy and sleepy. And I will have you answer a few questions about the Land Ice Working Group, and there's some prize to win here that Bill Lipscomb is going to deliver to the winner. So without further ado, the way you're going to enter the quiz here simply by scanning the QR code. Oh, no, you can't see it. All right, so if you can please scan this QR code, or you can also go to the kahoot.it mailing address and enter the PIN number, and then it's going to ask for you to choose a username. Username that's going to be semi-anonymous. And Lipscomb has kindly offered to not participate, to give someone else a chance to win. Nice. And please, if you're online, participate as well. If you're winning the prize, I will get it to you somehow. Don't you worry. I didn't choose the size of it. I'm sorry. Oh, there you go. Thank you. We just arrived. Scan this QR code to enter the game if you want to participate. Well, it's a combination of both, actually. You're going to see, anytime you answer a question, there's going to your name, your avatar here is going to see assigned points whether they answer correctly and how fast they have. All right. So, in the interest of time, is everybody okay here? How much knowledge you have about the Land Ice Working Group, CESM that you use often. Here we go. And so, yeah, look at your screen. The question is going to pop up here, but you're going to have to answer on your phone. Okay, first question. When was the Land Ice Working Group officially created? 2005, 2008, 2009, or 2011? And you have 20 seconds to answer each question. Ooh, one good answer. It was created in 2009, and the CSM chief scientist at the time was Peter Gent, who is sitting with us right now. So, about this Land Ice Working Group, at the time, the glaciology community was not very well connected with the Earth system. And this was a recollection from one of the first co-chair who was telling me that this is what started And this is how those big names like Tony Payne or Bob Binchadler got. So it was created under Peter Gent's leadership. Sorry, the first Amazon Rhino got it first, get it right. Peter Gent really create this, allows this working group to be created. So A, the cricket team has 12 players, or Tom Brady wore number 12. His favorite shape is a dodecahedron, or 12 divides in 3 or 4. Four good answers. Divides in 3 or 4, and it makes CSM workshops way nicer to plan. Mouse is taking the lead. All right. Next, how many people have served as Landis Working Group co-chairs this far? 5, 6, 7, or 8? The good answer was 5. Is taking the lead here. Here are the 5 working group co-chairs that have served this far. Bill Lipscomb, who's here, Jesse Johnson, who was a co-chair with Bill when everything started, Miriam Vizcaino, who's here, Jan Lennertz, who was a professor at CU, and myself. All right, what was one of the reasons CESM was a troublemaker to be added to CSM? It caused the Labrador Sea to freeze. It was too highly resolved, it took too long to build, or it broke the fixed boundary assumptions between the land, ocean, and atmosphere. Wow, look at you guys. 9 good answers. Indeed. CESM moved its boundary as it loses mass or gains mass, and this is not something CS happy with. Who's taking the lead now? Cute Koala is still in the lead. Wow. Outside of comments and empty lines, how many lines of code does CESM main contain? About 10,000, about 73,819, 100,000 or about 250,000 from 2 weeks ago. Ooh, no, it's about 100,000. Dove is taking the lead here. And this is a command that Brian Dobbins ran for me, and you can see here's a number of codes, actual codes, and the comment is about half of that. Next question. Which model first incorporated CESM as an iSheet model? NOR-ESM, CCSM4, CSM1, or CSM2? CSM1 is the right answer. Good, Koala is in the lead here. But still in top 3. And this is a picture of the CSM1 papers that was led by Jim Hurrell and Marika Hogan that showed the downscaling of the surface mass balance on. Now, CSM fully coupled has been used to simulate the last interglacial between 127 Ka and 119 Ka. Is this true or is this false? 8,000 years of fully coupled simulation. It is true. Rockstar Falcon is taking the lead. Wow. And this is a picture from the papers led by Alia Summers, who showed the result of those 8,000 years, which the green ice sheet was fully coupled and evolving and receded during that time. Next question, almost there. According to CESM, under current conditions, how much will Antarctica contribute to global sea level rise by 2100? Between -20 to 0 millimeters, between 10 and 60 millimeters, between 60 and 100 millimeters, or more than a meter? Is between 10 and 60 millimeters. Last question. Relative to today and under current conditions, how much volume of ice will the Alps lose by 2100 according to CESM again? About 10%, 20%, 40%, or 60%? Answer is about 40%. So let's see who's on the podium here. Number 3, Diligent Puffin. Who's Diligent Puffin? All right, Dave Bailey. Amazon Rhino. Number 2, who is Amazon Rhino? Someone online? Oh, okay. Who is Rockstar Falcon? All right, Kate. Come, can you stand up in front of everybody? Congratulations, Kate. All right. Thank you for indulging me in participating in this quiz. And I will now switch quickly to our short highlight. And I'm saying short just because I'm going to go through a few slides of highlights of our collaborators that couldn't be here today. And the other highlights will be given by our amazing speakers this afternoon. See, I will get it. All right. So first, I want to mention. I'm going to mention the work from Tim van den Akker, who is a graduate student at Utrecht University, who's about to graduate, and has been working with us in trying to investigate the influence of the current Antarctic ice sheet mass change rates on future force simulation. And typically, when we run CESM, we perform a spin-up first, and this spin-up is typically in equilibrium with the climate that we fit CESM. And it takes some time for CESM to get going when it's forced with climate forcings. And so we've developed this method that allows the mass change rates from Smith et al. And here, from this is oh. Okay, it's not working. Maybe my mouse is not okay. I will use my cursor, from Smith et al. Here, and by adding this method, we can get this mass change rates from the first time steps that we run CESM forward. And by adding, by investigating under different forcing scenarios that were used in ISMEP 6 for the West Antarctic ice sheet and Antarctic ice sheet, he concluded that the West Antarctic ice sheet could collapse between 50 to 100 years earlier if we're including those mass change rates, and the sea level contribution for the Antarctic ice sheet would double by 2100 if we included this mass change rate in our spin-up. So this is another initialization problem that's been identified during the ISMEP 6 results. Another initialization problem that we're working on, and with Tong Zhang, is about the geothermal heat flux. There are many different geothermal heat flux maps that are data sets that are out there, and we typically use one, but there's so many. And he's interested in investigating the impact that it has on the initialization of CESM. And here on the left-hand side, it shows a difference in thickness after using the same inversion procedure, but two different geothermal heat flux. And you can see that there's some thickness differences in some areas that varies pretty much between plus or minus 100 meters. And additionally, he's interested in looking into the influence of basal water on the slip boundary conditions in the basal sliding law. And he noticed that when you turn it on, it could have some non-negligible impact on the sliding itself, speeding up the ice sheet in some places and slowing it down in others. In terms of calving, so up to now, for at least Antarctica, we've been using a no advanced calving mask to have some sense of calving in our simulation. And more recently, Bill Lipscomb and Joanna Milstein have been working very hard on trying to incorporate a more realistic way of doing calving. And here was the first attempt to use horizontal stress-based calving that was also used in Mollingham 2016, but also in Lipscomb and 2019. And on the right-hand side here, you see the first 5,000-year spin-ups that Bill did, and the results of the extent of the floating ice using this calving law. It's work in progress, but it's already very promising. Now, there's some work here done by a collaborator, Tridata, who's at Delft right now, and she's interested in sources of extreme precipitation over Antarctica. And she does this by using CSM and the variable resolution CSM2 version, which increases the resolution over Antarctica. And then she added moisture tagging capability over multiple regions. And the concept of it is that here's what this map shows is like Antarctica is the center of the world. Of course it is. And then you can delimit some regions all around and tag those regions with this new code. And what it does is after you run your simulation, eventually you can focus on a region. In this example that you're seeing here, she focused on the Zwoli Basin, number 21, which is a basin that contains a Sweats Glacier in Antarctica. And for extreme precipitation, she was able to trace back where the moisture was coming from in this event over this basin. And the red line, the red color here means there's a strong origin that you can map to this region tagging that says, okay, well, the moisture originates mainly from the Western Pacific Ocean, especially between 35 degrees south and 55 degrees south. Next, we have some work done by Mira Berdal, and who is interested in the Southern Ocean and also investigating the warming of the Southern Ocean that could potentially make it to ice shelf cavities. In particular, there's a transect here that goes in the Amundsen Sea embayment under the Sweats Glacier. And she's comparing the high-resolution CSM1 model that is a 0.1 degree ocean and quarter degree atmosphere to a 2 degree low-resolution CSM2 model, and trying to investigate how the circumpolar deep water compared to modern evolves in this simulation. And so you have the high resolution on top and low resolution on the bottom, and a difference between modern and pre-industrial, and here for the future scenarios, the difference between the future and modern. And what she saw so far is that the lower resolution shows steady circumpolar deep water uplift and stronger subsurface warming in the future. But the magnitude in terms of warming, you can see there's some similar, except that there's this cooling here in the future, meaning that circumpolar deep water is having a hard time making it in the cavities. So this is still work in progress. We don't fully understand here what's going on, but what it means is that high resolution and low resolution ocean forcing would drive significantly different mass balance outcome if we were to use those with an evolving ice sheet model. And finally, here, this is some work by Charlotte Raves and Heiko Golzer. And Charlotte is interested in historically consistent mass loss projection of the Greenland ice sheet, in which she tried to use many different Earth system model and downscale them back using on the ice sheet grid in Greenland using the climate model MAR to then reproduce the historical forcing, the historical data set that, that we know, that for which we have some observation. And she found that using the right methodology, you could reproduce this historical state with these climate forcing, which you can then force into the future and get an idea of the state of the Greenland ice sheet by 2100. So as Dave mentioned this morning, there's a CSM survey that has been sent out on Thursday. I hope you received it. If you haven't, please let me know. It's a survey that is going to help us to characterize the value of CSM and its activity, including the model, the data, and support, and how these activities support a range of users and stakeholders and its delivering impact. There's a link here that we made available, so you'll have it. The survey takes about 10 minutes to fill up, and if you have any question, you can send them to Meg Fowler. Thank you very much, and thank you for your attention.
Oh, okay, cool. It's just appearing. Thank you. Thank you. Hey, everybody. So I am going to give this really quick talk, and it's totally different than all the other awesome science. Can you? Kind of short. All the other awesome science that you guys are going to hear today. Mostly because I mean, really, this is a software engineering talk, and so it could have gone into the software engineering working group, but you guys are our main science and software developers for CESM, so I wanted to get people on thinking about the idea of using CESM test framework during their CESM development. And so part of that is to be, you know, like excited, it's cool, it's awesome hacker stuff, so it's going to have lots of cyber illustrations here to make you all feel like you're into the computers, it's like in your brain, right? Okay. Or which button?
Yeah.
Vibrates?
Yes, vibrates.
Oh, okay, too far back. There you go. Okay, here we go. All right, so this is just what I'm going to talk about real quick. I want to talk about why CSM tests would help you. I'm going to give a quick rundown on how to run tests for CISM in CESM, but it's going to be a lot for 4 minutes or whatever I'm going to cover it with. So this presentation should be available to everybody afterwards, so you can go back and take a look at how to run the commands when you actually sit down to do this. It'll be in there. I'm going to give an overview of what tests are currently available and what plans we're going to have for the future. So running tests is always a good idea when you develop your model code. I think most people would agree with that, but some people get sort of into the science and the coding, and they may not remember that you need to run more generalized tests than just like trying to make sure what you're doing works. So of course, you can run a test to make sure the code, see if you have any errors that prevent building. You can see if your code changes answers that you don't expect. So if you think that you should be doing something that doesn't change answers in certain areas of the model, you can test to see if you've done that. And of course, maybe your code is producing unexpected side effects. So you might have worked really hard to implement this new Basel friction scheme, and then you run a test, and it turns out that you've broken any version of the model that isn't running active CESM. It's happened before. So running lots of different tests and lots of different configurations is always a really good idea. CESM has this really nice testing framework where you can do that with just a couple of commands. So this is just a quick overview. You're going to clone CESM wrapper, and up there at the top, do I have a pointer? I don't know. The very top. Okay, yeah. All right, so here we got like the first line is checking out CESM wrapper, and this is what it looks like. Next thing is to run git. You're going to go into that directory and run git fleximod, just like you would normally for using CESM for CESM wrapper. And then you go into the source CESM subdirectory, and you can check out your own code. And what I did here is I actually used my own fork. So a lot of people will put a branch on the ESComp CESM repository, which is fine, but you can also create your own fork and use that in your testing framework as well. So you just have to add a remote. And if this is kind of gibberish for you, that's totally fine. You can talk to me later, or you can just keep doing things the way you do. Eventually, you're going to check out your branch, which is down here. So git check out the CalDMIT PR in this area. Right. And then you move back to CESM testing, or CESM theme scripts, and you could run your test here with this create test command. This is a really important one here, create test. And you use a little code to describe what your test does. So this is a smoke test that runs for 1 year in debug mode on a low resolution grid using Antarctica and Greenland and a only CESM configuration. So those codes are kind of complicated, and I'll go over them more later, but you can also do this, which is to run a group of tests. So this is the aux GLC test group, and this runs a variety of tests in a variety of configurations to cover a large number of options. And this is really nice because it produces all of those tests for you in a single place, and you can go through and see how things worked. And then for each test, once you run it, you can run this little script that shows you a quick breakdown of how the test fared. So each test is going to produce a CS status. If you run the whole group of tests, there's one CS status that gives you all of the results in one spot. And you can actually grep through that for like the word overall, so you can see overall where you're at, which is really nice. For this test, this is great that I decided to do this presentation the week that all of the supercomputing resources were completely down. So I ran this on Izumi, and I discovered that it's not working. So it's crashing at runtime, something I'm going to have to look at when I get back. So C testing is good. It lets you know things that you wouldn't have expected otherwise. So right now, when you're running with CESM, the tests that we have available are Greenland at 4 kilometers, Antarctica at 8 kilometers, and you can run with CLM, so like an I case, or without, which is a T case, and that is just a straight CESM test. So we don't have quite the variability that you have with sort of the input, like regular CESM test suite, but we're working on adding all of those into the CESM structure as well. You can run with debug on and off, so yeah, and other configuration options are available. I didn't really show that, but at the end you can specify, a specific configuration file or test suite to make sure that your physics are being used. These are sort of some of the codes for the types of tests that we support right now. The smoke test is the one that I just showed you, where you run for just a certain number of years. You can do the exact restart, so it runs for like 4 time steps over 4 years, and then it'll run for 3 out in the future, and then run again for 3, and then compare those 2 to make sure that you're getting the same answers that you expect, which is really nice to do that all automatically for you and test that your restarts are working. There's a PFS performance test that'll give you lots of data on the actual performance of your code. Resource-wise, see how much memory and how many CPU cores are used and things along those lines. There's simple reproducibility tests that you can compare against baselines, produce baselines to compare against, and many others. So this is a link to the documentation on testing in CESM, which is very thorough. So if you're interested in this, that's a reference for the future. So we got plans for this. We want to expand it. We'd like this to be something that's easy as possible for people to use. I understand that this is a lot of like terminal stuff, so we're going to try to bring it into more general user group, but we're also going to try to make it more expansive and have options for lots of different parts of CISM to make it as useful as possible. So I'd love to hear from people. If you think this might be useful for you in your development and your science, please let me know. And that's all I've got, so only 2 minutes late. Run off the stage.
Yes, it's definitely useful. I wish I knew before because I started to do this a bit late. Just one thing from my specific user experience is that for the ERS test, at some point I didn't know how to, when you make XML changes to maybe have output more often, I couldn't know which simulation I was applying that XML change. I imagine maybe the one without restart. So I couldn't get for the restart test all the output after the restart. So I'm just saying that maybe there can be some more documentation or some more flexibility. That could be nice, yeah.
You edit the test defs file. So if you actually go into SEAM, and I can show you how to do this later offline, you can specify very specific test cases in certain directories, so you know exactly which XML things are being changed for which test that you run. So it might clear things up. So email me about that, and I'll talk to you about it more later. Yeah, that's all good.
Thank you, Kate. Our next speaker is online, and it is Robin Smith talking about ISMIP 7 for the coupled simulations.
Hi, everyone. Sorry, just getting the screen sharing set up. There we go. Can you all see and hear me?
We can see you, we can hear you.
Yeah, excellent. Cool. All right, so hello, everyone. Afternoon. For any of you who don't know me, my name is Robin. I'm part of the UK Earth System Modelling team, where I lead on the science and technical issues around how we model land ice. And pertinent for this, I'm also part of the ice sheet model intercomparison project for CMIP, known as ISMIP 7, where I'm on the steering committee. So I'm going to talk about ISMIP 7 and very specifically a couple of activities in there around Earth system models that have coupling with ice sheets, like CESM does. So thank you for inviting me, and I hope that's actually what you actually wanted to hear about. So I've got a link up there and a QR code that goes to the same place. That goes to a shared drive that's being used by the ISMIP 7 ESM ISM group. I think it's open access for anyone that wants to see it. So there's some documents in there with more details about all of the things I'm going to talk about today. I'm not going to go through all of the gory details, so you can go and see them there, or you can contact me, or yeah, anything. All right, so let's start with the basics. For anyone who doesn't know what ISMIP 7 is, here is our mission statement and core activity from our new website. So go and check out our new website as well. Basically, ISMIP 7 is there to make sea level projections that are consistent with and driven by CMIP climate projections. So the main way we do that is by taking climate and boundary conditions from the CMIP scenario it runs and running standalone ice sheet models. But you'll notice there that there's also mention of coupled Earth system models. Now, there's not many CMIP class models that have had coupled ice sheets in them up till now. CSM, of course, was a trailblazer with your green coupling in that regard. ESMs are pretty expensive. There's issues with the coupling with the ice sheets around the time and space scales. That means that CMIP ESMs are not really the best tool for the sort of ice sheet modeling that we want to do here, which raises the obvious question: why are we talking about ESMs? Why are we talking about doing ice sheet modeling in this context?
Robin, I'm sorry to interrupt you.
Yes.
Could you attempt to reshare your screen? We're getting cut off on our end slightly. Mostly the margins on the side, left and right.
tell?
Yes.
That's
Yes?
better.
Fantastic. Thank you, Robin.
All right, so there's the mission statement. If you were missing the first few words of that, you can go to the website and see that again. And I guess I can skip over this really quickly because I assume most people in the room know why you might want to have ice sheets inside an ESM, since we're talking about CESM. There's changes to the local climate that change the boundary forcings as the ice sheet evolves, so you might get a different mass loss projections on the ice sheet, or at least it might be sensitive to those changes in particular places or over particular timescales. And then we're interested in the rest of the Earth system as well. You don't have to get quite as extreme as the tipping point problem to know that freshwater flux off the ice sheets is an important part of the Earth system. If we're not modeling how that changes as our scenarios go along, we might be missing something in our climate projections. But in the particular CESM context, so most of our sea level projections, like I said, are coming from those standalone ice sheet models. But the ESM model experiments there with the coupled ISMs are not primarily to produce projection numbers. They are to look more mechanistically at when, where, and how the ice sheet coupling becomes important for the projection of the ice sheet mass loss and climate. Where are the projections that we're getting from our standalone ice sheet models going to be becoming inaccurate because we're missing out on those feedbacks with how the boundary conditions evolve? Where do the climate models need to know about the changing freshwater flux, importantly? So we are doing a bit of sort of historical comparison, a little bit of evaluation against observations, but mainly what we're doing here is trying to gain physical understanding into the system as a whole to supplement what we get out of those standalone runs in terms of knowledge about the uncertainty around the sea level projections. So that brings me to two particular activities that we're doing in ISMIP7. So the first of them is not actually a MIP at all. It's the idea of this focus group. It's this community group that we're setting up. So there aren't that many ESMs that have these coupled ice sheets in at the moment, but there's a big interest in it. Most of the modeling groups have got a certain amount of effort put towards seeing what they can do in this area or where it's important for them. So we're running a little bit of a sort of community capacity building exercise. We have a mailing list with about 50 people on it. We've got representatives from quite a lot of the modeling centers with particular interest from those ones listed at the bottom. And we have every few months or so, there's an online meeting. We have a bit of a discussion. The idea really is to be a knowledge exchange, help people who are still developing come up with ways of dealing with their problems, just raising awareness of the sort of practical problems we get coupling ice sheet models into Earth sheet models, Earth system models, and of course work out issues around the experimental protocol that we're going to have in ISMIP7, because we are going to have some simulations and a protocol for ESMs with coupled ice sheet models in them to run to help us understand where the coupling becomes important for our projections. So in the protocol, say about this one? Well, fairly obviously then, in the protocol, we've got two types of experiment. We've got the ones where we have got the interactive ice sheets running and the ones where we haven't. Simply compare those two things against each other, and that will start showing us where the coupling is important in particular models. So I'll run through some of the details of that protocol now, hopefully leaving enough time for some questions at the end. Like I said, if you want to know all the really gory details, you can go and find that on the web or come and ask me afterwards. So the basic tier 1 experiment is a control experiment and then an idealized warming that goes with that. Those can be fairly short. I'll list some of the timescales later. We're basing this off a 1950s baseline rather than 1850. As you know, there are all sorts of issues around initializing ice sheets, what pre-industrial ice sheets might have looked like. 1950 is sort of cutting the difference between what the ESMs want to do in terms of going back into the historical and coming up to the future, and maybe what some of the ice sheet models that do a modern initialization can cope with. The lower tiers, we get into doing things that look more like, or less idealized, that have a historical experiment, again, really just from 1950, but if you run that from 1850, because that's how the rest of your ESM works, that's fine. And then some of these scenario MIP scenarios where I've been deliberately vague here about exactly which scenario MIP one was we're talking about, mainly because those specifications weren't available when we started this. We're not being prescriptive about whether you run with just Greenland or just Antarctica or both. Both, if your system can do it, that's great. But people who can only do one or the other are equally welcome. So we are starting with this protocol now. So we're doing some demonstration simulations with the models that can. Timescale wise, we're not trying to do this as part of the fast track. We want to aim for this to be one of those sort of later community MIPs, really because a lot of the models aren't actually ready to do this yet. The trouble, of course, is the IPCC deadlines that we also don't quite know yet, but we would like to have some things ready and publishable for then. And we do actually have a little bit of funding for a postdoc to help analyze some of these results through 27 and 28. So some results sooner would be better, and those we'll be able to leverage them a little bit more. So this is just a quick look at what the current suggestion for scenario MIP scenarios are. The main sort of scenario MIP runs to 2100, 2125 are interesting, and that is the shortest timescale we'll look at. But obviously for the ice sheets, we are interested in the much longer timescales. There's still a bit of it's still not entirely clear what's happening with the overshoots and the extensions, particularly for these H1s. So we haven't nailed down in the protocol exactly which is going to be our sort of high priority tier 2 ice scenario, but it's probably going to be something that looks like the HXOS line on this graph, depending on where scenario MIP ends up. There'll also be a low scenario, which is likely to be this VLL01. And those will be the same between the ISMIP standalone ice sheet experiment and the coupled ones, just so we can compare between them. This is a quick flash up of one of those gory detailed slides. So if you go to that Google Drive, or I can point you to this, we have got recommendations for sort of minimum lengths of runs, minimum number of ensemble members for each of these different things. But like I said, we're not being enormously prescriptive. We recognize that there aren't that many models yet that can do this. We do just want to encourage people to do what they can and join in. So another area where this has actually been a bit trickier than we thought. So the defining model configurations and experiments for when you've got interactive ice sheets is kind of easy. We just tell people to switch on everything that they've got. There's comparison experiments where we want to have them switch off the ice sheets in those configurations have actually been quite difficult to define. Different ESMs sort of structurally mean different things by turning off their ice sheets. And just having geometry changes turn off doesn't produce very much of a signal and often doesn't really reflect the changes in freshwater fluxes and the sort of the different physics that are available in some of these models. So for without ISM in this sense, we've defined the ideal goal of that as not changing the geometry and keeping all the freshwater fluxes sort of at control levels and not letting them change through the experiments as well. There's a lot of implications for that. And like I said, we're asking for people to do the best they can along those lines, and we're not going to sort of turn anyone away if they don't meet all of those criteria. So like I said, we've got some demonstration runs with a few models that can already do them starting now. Those are going in the protocol paper that we're writing up already. We don't just want these for showing some demonstration results and that our protocol is possible. Like I said, like it says here, we have got a few sort of subtexts and things I think we feel as a community we need to show to the rest of the ESM world. Basically that it's worth doing this, that it's possible to do runs like this with interactive ice sheets. And that it does tell us something useful in the end. So we think likely we'll have some sort of draft results from these 5 models listed at the bottom in that protocol paper that we're working on now. I thought I should flash up the CMIP timeline since that's obviously relevant here. It's all somewhat provisional because the IPCC timeline isn't exactly set up, but it is worth noting that we have got ISMIP there as an official box between 26 and 27. So this is ISMIP as an activity has got a lot of interest from CMIP this time round. People are very interested in getting results out of us and these sea level projections that we can do. So I think it's likely to be a fairly high profile thing. But in the interest of time, I will stop there. And if anyone's got any questions, you can ask, or there are the links for the Drive stuff there.
Thank you so much. Do we have any question? Okay. Yes. Okay.
Hi, thanks for the talk. I have one question. Thinking that in the future, more model participating to CMIP will also start to include ice sheet model coupling. How do you think, compared to this initial work of looking at the physics and interaction, how we can then make, tune the model in such a way that simulations are more realistic? And if you think that that would affect a bit the interaction between the Earth system model and the ice sheet model, and if you see any possible problem in that?
Let me think. So, I mean, what we're seeing in a lot of the models that we have at the moment, I guess, are that the regional climate biases around the ice sheets are really affecting how well the ice sheet simulation is going in those senses. So, I mean, I think there's a long way to go before people are using them sort of as regular parts of the model. Initialization, I mean, getting things to the point where so they're initialized, they're starting in the right places and evolving in the right way through the historical, I think is key, really. I think we've got a long way to go to prove that we can really do sort of historical stuff. That means we can evaluate how well these things really are working. I think that's going to be key to getting wider acceptance of whether we can have ice sheets in these models for sort of more standard runs and that people accept the results from them. Does that answer? Is that relevant?
Thank you, Robin. We are going to go to the next speaker, who is in the room, Kai-Xuan Khan, and she's going to give a GAI presentation.
Hi, everybody. So today I will talk about the, how can I say my slide? Today I will talk about the topic about the interaction between the solid Earth and ice sheet evolution in Antarctica. Yeah, especially I will talk about the effect of the lateral viscosity variations in the Earth, or the local sea level and bedrock motion in Antarctica. I mostly will focus on the Antarctica deglaciation history since last glacier maximum, like shown here in the top frame, the ice cover change since from last glacier maximum to present day for the northern and southern hemisphere. And I will use numerical model to simulate how the fluid mechanics in the Earth counting for the more complex Earth structure and how this can impact the local sea level and bedrock motion, which are two of the fundamental conditions for the ice dynamic modeling. And here I show the global sea level change since last glacier maximum. You can see the alternating slow and fast sea level rise during this deglaciation period. And we can focus on, for example, the meltwater pulse 1A, which is the significant sea level rise globally, 16 meters. And from one of the model available from the Argus in Antarctica, you can see they also just contribute to this global sea level change. And you can see the margin, mostly the ice loss focuses on the coastline of the Antarctica peninsula. And move to the next meltwater pulse 1B around 11,000 years ago, you can see the Antarctica dramatically contribute to the global sea level as 5 meters in 300 years. This is dramatically, you can see the ice loss throughout all of the West Antarctica sheet, especially in the raw ice sheet, and now in the raw ice shelf, and also one of the interior of the West Antarctica around the Whitmore Mountains. And more recent is meltwater 1C is a little bit mild sea level rise around 1 meter, and I will show how the solid Earth can respond to this different kind of 3 meltwater pulse events, which show different ice dynamics response to the climate forcing. To do this simulation, I really need the 3D numerical model package, like the sitcom SVE developed my PhD advisor, Professor Zhong, and we counting for this very complicated Earth model. I show here two of the many Earth model, and the first is Texas 19, and then the Reveal. So by eyeball, you can see these differences between these two viscosity model. One is the resolution. One lower resolution, more smooth change, and another is just a very high resolution, which will give more details, more short wavelength structures in the Earth model. And another is the horizontal gradient change in the lateral viscosity variations. In the top, Texas 19, they will give, in the shallower one, in the shallower depth, they will give a large contrast between the West Antarctica and the East Antarctica. But the Reveal one with higher resolution, this kind of contrast is less. So we will use a numerical model to test how these two different viscosity model can affect the sea level and bedrock motion in Antarctica. And now come to the results. I show first for the meltwater pulse 1A. I show the right top is the ice change rate during this period, and the left panel is for 1D, the first column, and two 3D models, the second or third. And I give two time period. For the top one, the 14,000 years ago, you can see the dramatical ice, not dramatical, but the ice loss around the South Antarctica coastline, the peninsula, they will just induce the land uplift, the land motion uplift correlated with, share the same spatial pattern. And the 3D model, which they have the more lower viscosity in the north, in the West Antarctica, they will give more gradients in this land motion. And after 5 years, and then we will focus. There's no ice melting from the East Antarctica, but from those land motion, we see the East Antarctica, they are just subsidence. This show the interaction between the northern hemisphere ice melting. They just influence from each other. For example, I show the global map. You can see there's huge subsidence near the East Antarctica. Actually, this is caused by the polar water, which when the Earth, when the global mass redistribution globally, and then they will trigger the polar position. They will just water a little bit. They will deform the whole Earth. So you can say this will deform the east coast of the east Antarctica around the coast. So yeah, another is just the sea level fingerprint. I think they evaluate from Gomez's recent paper, so the global sea level rise. So from North Hemisphere will affect the ice dynamic in the Antarctica during this period. And when we move to the rapid ice melting event in Antarctica, particularly for the meltwater pulse 1b, we can see there show significant difference when we use 1D and 3D. And first, when we use 3D and we introduce a larger both vertical and horizontal motion in the West Antarctica, there is you can see the blue. You can see the blue color showed in the 3D model, but they're missed in the 1D model. This is really caused by the contrast, the horizontal gradient in viscosity in the West Antarctica, this structure. So if we want to capture those kind of complexity in the Earth model, we need to use 3D. So 1D just missed this process. And also the horizontal, motion. Also I think the blue color which 1D model missed is the peripheral boat. So this will affect the marine ice sheet dynamic instability, I think. When we move forward for another very mild ice loss meltwater pulse 1c around 8,000 years ago, and we can see the spatial pattern from the solid Earth bedrock uplift. The spatial pattern is still very similar to the ice loss during this period, and the amplitude is muted because the ice loss is also less than the previous two meltwater pulse events. Between 1D and 3D, we can see 3D still just produce a larger signal in vertical. I mean the bedrock uplift, but horizontal motion almost like kind of in the same scale. And here I show the relative sea level evolution through the time. I pick up 3 sites. The first 2 sites is located in the West Antarctica, and the last one is from the East Antarctica. You can see the sea level curve. They show different time features. For the West Antarctica, they just show sea level rise and then just go sea level down. Sea level fall since 11,000 years ago, but for the East Antarctica, just keep the sea level rise until 8,000 years ago and just mild sea level fall. This is tell us. I think this is tell us maybe the different ice dynamic processes happened between the East and West Antarctica ice sheet. For example, the local sea level mainly controlled by 2 factors. One is the sea level. One is from the sea level. I mean the sea level source from the northern hemisphere, and another is just the local Antarctica ice melting contribution. So these 2 factors just compete with each other during this period. You can say if we just see first the 14,000 years ago, both the West and East Antarctica, they just show sea level rise. This is mostly caused by the dramatically ice loss in the northern hemisphere. So the Laurentian and the Fennoscandian ice sheet just melting dramatically. This will introduce a huge amount of sea level rise for the Antarctica area, and then when we go to the meltwater pulse 1b around 11,000 years ago, I think due to some interaction between due to the ice dynamic process, the West Antarctica, most of the cities below the sea level, they're more sensitive to the sea level rise. So they start to just have more melting locally, and this ice melting locally will just uplift, make the bedrock uplift, so the local sea level start to fall. This is one factor to call this sea level fall since 11,000 years ago. Another is the local sea level decrease since the deduction in gravitational forces from the melting water, from the ice loss. These two factors give more sea level fall around West Antarctica compared to the sea level rise coming from northern hemisphere. So for West Antarctica, for the Moran ice sheet, they just change from sea level rise to the sea level fall since 11,000 years ago. But for the Eastern Antarctica, you can see it's more stable. So the sea level rise continues, and the local ice sheet cannot compete those kind of factor. And I will go to my last slides, the future plan. So by so far, I think there's two fundamental methods for construction ice sheet evolution. One is the more recently developed. They use the ice dynamics and GIA coupled model. They introduce the ice physical law into the GIA models to couple. Like I showed here from Gomez group, their reconstruction the Antarctica ice sheet around 14,000 years ago and 11,000 years ago. And another is what I showed in my previous slides is from the traditional GIA model with geological and geodetic data contrasts. It's very interesting. You can see when we compare these two ice models, especially around 11,000 years ago, we can see the spatial pattern is so different. When we include the ice dynamics, the Ross Sea ice just melting more. But when we just ignore this physical law, but use only the GIA model to fit the data, and the way resulting in ice melting around those interior of the West Antarctica, which around the Whitmore Mountains. So which one is realistic? We don't know, but we think they both are realistic partially, because the first one, the top one, they speaks to the physical law, but the second one, they speak to the data observations. So the future plan is really we want to explore how to reconsistent Antarctica deglaciation history, build this model that can both follow the ice dynamic physical law, and at the same time they can fit the geological and geodetic data observations. So I think this will they will significantly improve the uncertainties in the Antarctica ice sheet model. Like I showed here, the uncertainty right now is so huge between different models. So thank you so much.
Thank you very much. In the interest of time, we are going to move to the next speaker, who is remote, Saina Sadai, on Antarctic meltwater and projections of future sea level.
Make this smaller and hide this. Okay. Hey everyone, thanks for having me. I am going to be sharing some work that's from the last chapter of my dissertation. I worked on this with Ambrish Karmalkar, David Pollard, Yue Dong, Erica Lucas, Natalia Gomez, Raja Kanto, and Alan Condren. Okay, here we go. Sorry, the Zoom window was doing something weird. Okay, yeah, so I'm going to be talking about Antarctica's evolution under different greenhouse gas forcing scenarios and impacts in just these two models that we've coupled in this work here. So the broader importance, Antarctica is obviously losing mass. There's some GRACE data from recent years, and this has impacts on local and global climate. Antarctica is also a primary driver of sea level rise, and that is expected to continue into the future. And this all has broad, wide-reaching impacts on society, but of course, it's really challenging to model marine-based ice sheets. It's hard to represent a lot of those dynamics, and pinning down the interactions and feedbacks between the ice sheet and the ocean and solid earth and atmosphere is particularly tricky. And so as efforts to integrate dynamic marine-based ice sheets into global climate models continue, ad hoc freshwater forcing and coupling experiments are sort of filling this gap to understand some model responses, and a lot of work has been done on this. This is a out-of-date and incomplete list at this point in time, but there's been a lot of work done over the years. And I am taking a kind of different approach to this talk today. I'm doing something really experimental and taking more of a storytelling approach, because I think when I was a graduate student, I would have really loved to hear about how collaborations are built and how work gets done, and like how ideas and simulations and things evolve. So I'm taking a bit of a storytelling approach here about the work that I'm presenting today. So I started my PhD way back in 2015, about 1 million years ago at this point, even though it was only 10 years ago. And I was doing meltwater forcing experiments with CESM1, and I was taking meltwater output from the Penn State University ice sheet model and feeding it into CESM as one long time series, a couple centuries, feeding that into CESM and seeing how the model responded. And I want to point out here that federal funding and support from NSF and NCAR was absolutely crucial to all of the work that I did as a PhD student. And I spoke about this at the Weather and Climate live stream a few weeks ago. Probably many of you also gave talks as well, and those recordings will be up soon. But federal funding is crucial, and the impacts that are happening right now as federal funding cuts continue are very detrimental to the scientific research in the US, and also our collaborations that we have with other folks. So just wanted to mention that. In 2020, my first dissertation chapter was published, and it was looking at those initial CESM meltwater forcing experiments. And we found delayed surface air temperature rise, but increased subsurface warming in the Southern Ocean. And obviously, the changes that meltwater induced in the climate would have had impacts on ice sheet evolution, but because we were just taking the meltwater and giving it to CESM, we couldn't capture any of that in that first bit of work, but it was something that we wanted to do for the future. Science is better with friends. As I went through my PhD, I met a lot of amazing people. And after that first chapter was published, Dr. Yue Dong reached out to me and was really interested in thinking about Antarctic meltwater and the impacts that it has on this delayed global mean surface temperature rise. And so Yue asked for some of my data from my PhD work and Andrew Pauling's data from his PhD work on CESM and meltwater forcing, and wrote this beautiful paper looking at why Antarctic meltwater reduces transient warming and climate sensitivity. And we're going to return to that in a few minutes. And I also met and started collaborating with Dr. Gomez at McGill in Canada, who works a lot on GIA and sea level modeling to get at the spatial fingerprints of Antarctic mass loss. And so after I did that first chapter, I did something completely different and researched the climate justice implications under the UNFCCC of spatially variable and long-term sea level rise, and simultaneously meltwater feedbacks on global mean surface temperature. And I wanted to investigate those two things together and to really think about the ways that gravitational, rotational, and Earth deformational effects have this spatial fingerprint on sea level. And this is the spatial fingerprint of Antarctic sourced sea level rise impacting members of the Alliance of Small Island States. And so this work was another thing that was in the background as we got into our coupling experiments. Also, when I spoke at the CESM workshop last year, I talked about the importance of GIA and ice sheet model coupling and also sea level science informing climate litigation. But I wanted to give a shout out to this amazing poster last week at the GIA workshop, where a bunch of y'all are working on modeling GIA in CESM. And I thought this was amazing. And so I just wanted to give a quick shout out that it's really cool. And I was excited to see this. I'm going to get to the science real soon. But in 2019, I started the final chapter of my PhD work, which after those initial CESM meltwater forcing experiments and then the foray into climate justice philosophy, I came back and started working on trying to interactively couple CESM1 and the Penn State University ice sheet model. This was a beast of a problem, but I did get it successfully up and running in 2021, finished my RCP 8.5 simulations and model validation in time for my defense, successfully defended, and graduated with my PhD in 2022. And so using CESM1 and PSU 3D together for the interactive coupling, it builds upon the earlier work, but there's a lot of differences here. So every model year, PSU 3D is providing meltwater quantities to CESM, and CESM is masked out, sorry folks, to avoid double counting, obviously. And then CESM1 is passing to PSU 3D the air temperature at 2 meters, the ocean temperature at 400 meters depth, which is the depth at which PSU 3D takes in ocean temperatures, and then precipitation fields. And to check if this was working well and to do a little bit of model validation, we checked the coupling experiments against calving and basal melt rates around the full ice sheet, basal melt rates at particular locations, total annual change in mass and global mean sea level rise contribution, and then the spatial patterns of ice sheet thickness. And when we had something that worked pretty well, we ran the projections forward. And so in 2023, 1 year post-graduation, I started building out the collaboration for what I wanted for this paper, because I wanted to bring in the other friends that I had met along the way, and to bring in GIA and sea level modeling, and also the radiative feedback analysis. And so that's what led to the group of people that are co-authors on this work on Antarctic meltwater altering future projections of climate and sea level. Wrestled through that RCP 4.5 simulation during the Cheyenne decommissioning. I think we all remember what fun that was. And so what we ended up with in this paper is ice sheet plus climate plus GIA models, and also radiative feedback analysis. And so, as I said, CESM1 and PSU 3D are exchanging information interactively every model year within these simulations, starting from around 2005. And then there's an offline coupling to a 3D viscoelastic Earth structure model to account for GIA and spatial sea level change. That is done after the fact. So after the interactive simulations between PSU and CESM, then the offline coupling to the viscoelastic Earth structure model happens. So we are not interactively coupling the changes in the ice sheet and the GIA. We do have another paper on that, Gomez 2024. But that wasn't in this particular work. And then the radiative feedback analysis as well. A few additional details on the coupling. So it's surface only meltwater forcing, and PSU partitions mass loss into liquid and solid discharge fields. And those are spatially variable around the ice sheet. So it's interpolated wherever PSU is predicting the melt is coming out of, that's interpolated into CESM to get it to the next closest ocean grid cell, and then it's annually evolving. The ocean temperatures from POP2 are bias corrected, and those are extrapolated under the floating ice shelves in PSU 3D, and there's a single average value per each floating ice shelf every year. This was the biggest beast of trying to get this to work, because initial simulations just led to catastrophic collapse of the Ross ice shelf, which is in like the year 2020, which is not It's not physically realistic. But so we did end up with something that matched observations pretty well in the end though. But this one line was like a year of my life or two. And then the temperature and precipitation are lapse rate corrected in PSU 3D as the ice sheet surface evolves. And I want to point out here and stress that there was only a single ensemble member per emission scenario. One interactive coupling for RCP 8.5, one interactive coupling for RCP 4.5 due to computational constraints. So we're not getting at all at internal variability here. We're not able to do like a robust statistical analysis or anything. It's just for the interest of how these two models co-evolve when run in this manner. And here's some look at the ice sheet model output. So this is under RCP 4.5 at 2100. You can see that Thwaites starts to get lost a little bit there, and there's some thinning out in the larger ice shelves. And then by the year 2200, there's a much more large-scale waste collapse and additional thinning within the large ice shelves, with just a little bit of mass loss happening from East Antarctica. And then under RCP 8.5, it's the same sort of spatial pattern, but more loss of ice at 2100 and a much different picture at the year 2200, where we have far more mass loss coming from East Antarctica. And so to put these two side by side, RCP 4.5 and 8.5, both at 2200, there's about a 1 meter global mean sea level rise contribution from Antarctica under RCP 4.5 and a 3.37 meter contribution under RCP 8.5. And then the main difference there is coming from East Antarctica, because there's so much mass loss under the higher emission scenario. And looking at these in a time series, so this is out to 2100, the East Antarctic ice sheet in this interactive coupled simulation actually contributes more to global mean sea level rise by 2100 than the West Antarctic ice sheet does under RCP 8.5. And by 2200, they're contributing approximately equally to the global mean sea level rise contribution. But under RCP 4.5, the East Antarctic ice sheet is mostly relatively stable, and waste is what's really contributing to the global mean sea level rise signal. When comparing this to earlier work where in my first chapter, we ended up feeding in the meltwater perturbed climatology into PSU 3D for a standalone simulation, finding that the meltwater forcing delays ice sheet mass loss, we found in this interactive coupling, it further delays the ice sheet mass loss. So there's a lower global mean sea level contribution in the interactive coupling than when we use the meltwater perturbed climatology to run PSU 3D standalone. To compare this with some other recent coupling experiments in Park et al., which was using the same ice sheet model but a different climate model, they also found that the meltwater forcing delayed ice sheet mass loss. In the CG1 paper, et al. Paper from 2022, they found a sea level fall under RCP 8.5 by 2100 using both a different climate model and a different ice sheet model. So all of these divergent trajectories really show the need for comparing responses across models, as Dr. Smith was talking about a few talks earlier. And then to look at the spatial fingerprint of Antarctic sea level rise. This is under RCP 4.5, and the purple line here is everywhere where the global mean sea level contribution from Antarctica is what's being experienced and mapped out. And then everywhere above that purple line are places that are experiencing more than the global mean sea level contribution. And then so the difference there being from global mean sea level to the highest impact regions are 0.3 meters. And there's a higher impact in all of the ocean basins, Indian Ocean, Pacific, and Atlantic. And then under RCP 8.5, there is a different sort of spatial distribution for the most impacted areas. And that is because of that changing spatial distribution of the mass loss, with a much larger contribution coming from East Antarctica. And here, obviously, the GMSLR response is much higher in a higher emission scenario. And so the difference between the regions experiencing GMSLR and the regions experiencing higher than that, the highest impact is 0.9 meters higher regional sea level in the Pacific and the center of the Atlantic Ocean basin. to look at some CESM output. These are the surface air temperatures at 2 meters. These are the difference between the interactive coupled simulation and the control simulation. And we find a delayed GMST rise of about 0.3 degrees Celsius. So the interactive coupled runs are about 0.3 degrees Celsius.
You have 1 more minute, if you can wrap up. Thank you.
Sorry. So the radiative feedback analysis shows that this is from more efficient deep ocean heat storage, from increased stratification, and lower effective climate sensitivity from the reduced surface cooling and teleconnections. And we also have this bipolar effect here where there's enhanced warming in the northern hemisphere. There's also other things we looked at here that you can read about if the paper comes. So we submitted this paper to peer review in January 2024. It got 3 desk rejections in 4 months, and it's currently in the 3rd round of peer review. I sincerely hope it'll be published at some point. So yeah, ad hoc coupling can help us learn about Earth system responses, while the important work of incorporating marine-based ice sheets into GIA models, into climate models continues. I am also currently 3 weeks out from unemployment and on the job market, so please pass along anything you hear of that might be helpful for me. But yeah, thank you all so much for your time.
Ute, you have a question? Very quick. Don't hurry.
Questions. Interesting talk. I have one question under 4.5. When you have less emissions, you actually have a higher result of melt in the Amundsen Sea embayment than with 8.5. How would you interpret that?
Do you mean on
You had these
which?
melt maps for 2,100, 2,200, right? If you go back to that, you see ASE is really high for the lower emission than for the higher emission.
Here?
That, yeah, so it's really high. So now you go to the next map. Keep going. A really small melt blob only before.
Really small.
Now I don't see it anymore. Yeah, so like there with 8.5, you have really tiny responses on the left. That's what I was wondering about.
This part? Sorry, can you repeat the question?
Yeah, so if you look at this map, there's really little response over the Amundsen Sea embayment, which is where Pine Island Glacier is and so forth. But with the lower emissions and probably higher temperatures, there's more. All your conclusions.
Sorry, I'm really not getting the sound
Never
coming
mind
through
then.
that well. Can you email me with the question, and I would be very happy
I mean,
to
on
respond.
these,
I'm
you
sorry,
have
I'm
really
not.
high results, and then if you go to the next one, you have a low melt rate for. No, it's not. Anyway.
In the ice. I'm sorry, I'm not quite getting the question.
Whether you have, sorry, do you have a map for 2100 for the 4.5 scenario?
Yeah, see like to the left, see how.
See, the response for 4.5 seems larger than 8.5.
The melt rates for 4.5. These are ice thickness change maps. It's not quite getting at exactly the melt rate. It's how much the ice thickness has changed by that point in time in that simulation.
I think we are gonna.
Never mind, we can leave.
Yeah, I think we are gonna follow up offline. Yeah, thank you so much. Our last speaker is remote, and is gonna talk about actionable science. Is David Bihar.
Okay, hi everybody, can you hear? Well, I'm not going to ask any questions. I'll just plunge right in. Can you see this?
Everything is going well.
Okay, good. So I'm a practitioner I'm standing between you and coffee, so I'll try to go as quickly as I can. If there's time for questions, great. I've been in the science to action space, working with scientists and practitioners to understand where sea level rise projections are going in particular. And this is an update on the latest work that I've been doing with some of your colleagues on this subject. It follows a conversation or a talk I gave at a CESM workshop almost exactly 15 years ago. And it was that talk was focused on collaborative climate science, a user perspective on need, communication, and adaptation. And I talked about how though scientists and practitioners are very different species from one another, we have the ability to work together to create a symbiotic relationship. We need your work to adapt to the impacts of climate change, among other things. And so it's very much in our interest that we work on this. The other thing I did in that talk 15 years ago was show a definition of actionable science that the Water Utility Climate Alliance had created just the year before. Water Utility Climate Alliance is a collaborative of water managers that are concerned about the impacts of climate change on our supply. And we defined actionable science as data analysis and forecasts that are sufficiently predictive, accepted, and understandable to support decision-making, including capital investment decision-making. That last phrase was to emphasize the huge financial stakes that I think we're all aware of in the adaptation enterprise. But one of the things we didn't do well there, and that I would argue has not been done particularly well, or certainly not in a conclusive way since then, is to define what sufficiently accepted means. Actionable science is intended to be different than peer review science. We would argue that you can't take every new paper that comes out and adjust your thinking about your adaptation work without having some kind of understanding of what's been accepted within the science community to some degree or another. Parenthetically, very quickly, I'll come back to this, but there's a new collaborative, the Practitioner Exchange for Effective Response to Sea Level Rise, which is global in nature, focused on coastal resilience issues with 600 members in 60 countries. I'm the chair of that. It's another place where this science to action conversation is incredibly relevant, and that's why I'll come back to them toward the end. The most recent update in this work is a paper in the Cryosphere in 2025 that I was privileged to work on with two of your colleagues, Bill Lipscomb and Monica Morrison. And it was focused on sea level rise projections, adaptation planning, and actionable science. And really what we focused in on, as you might expect, is land ice. And we looked at the case study of the Decano and Pollard 2016 paper, which I'll come back to in a moment, to learn about where actionable science is and how we might be able to take this conversation and advance it a little bit beyond from where it has been. Where it's been, in many ways, has been somewhat confusing. This is a chart from McInnes et al. In 2024, and the green line shows median sea level rise projections, global mean sea level rise projections across the 12-year period from 11-year period from 2012 to 2022. Almost no change. Pretty consistent across the 11-year period, while at the same time looking at RCP 8.5 or SSP 585, 2100 numbers, and kind of the high end of the tail of projections, or the far end of the high end projections, you can see that upper end or high end sea level rise has been up and down, up and down, up and down during that same period. This has largely been driven by the changes in understanding of land ice that has been occurring, as it should in the scientific world, of course, evolving quite a bit over that period. This doesn't tell the whole story, because when you look at regional projections, this is the regional projection for California that came out of the Sweet et al. Federal Interagency Report, 3.1 meters in 2100. So it's even more of a swing for those of us in California and other places that looked at regional projections that came out of this fluctuation in the global mean sea level projections. This is what Andy Revkin in the New York Times, in an article that was actually about land ice melt, significantly called the whiplash effect. And a scientist observed that sometimes scientists, and I think also journalists, fail to carefully discriminate between what is well understood and what remains uncertain. And this dynamic has contributed to a chaotic environment in the practitioner community. This is the first ever global survey of coastal adaptation practitioners, 253 of whom responded to a survey that I worked on with Daniela Hirschfeld and 25 other authors that appeared in Communication, Earth, and Environment in 2023. And there are a lot of findings. We asked people, what projections are you using in planning? There's a lot of findings in that paper that I'm not going to go over. But at the high end, what we saw was a lot of folks were using a high-end number of less than a meter for their planning in 2100. And some people were using numbers as high as over 3 meters. So that's evidence that there is a failure to communicate how to use this, how to use the scientific information or opus as it exists at any given time in planning, because these are differences that are not explained by regional differences in the way sea level rise plays out. And so there's a problem, and we need to address it and find a solution. Going back to the Water Utility Climate Alliance actionable science definition, there has been progress in the literature to expand on this. This is Stammer et al. From 2019, written by 8 sea level rise scientists and a couple of practitioners to look at the long tail of the PDF, combining all RCPs. What do we do with this long tail? Is everything along the tail actionable information, or should we differentiate between projections that have multiple lines of evidence for high-end sea level rise in the planet, and those that kind of explore plausible physical limits at the far right end? And the conclusion that we gave was that finding where this bar is helps us to understand what actionable science is and isn't. Another paper in 2022, Vanderwall et al. Advanced this concept quite a bit. This was 25 sea level rise scientists from around the world and 3 practitioners. I was part of both of these papers, as were members of the Army Corps of Engineers at the time. And Vanderwall said, let's look, when we're looking for high-end estimates for practitioners, for science that has multiple lines of evidence rather than single sources behind it, strong confidence in the science community rather than weak confidence, and a plausible high end. There's that word plausible again, which I think is actually quite ambiguous. But looking for a plausible high end rather than the worst imaginable high end that's drawn from UK and Army Corps policy. And then the most recent contribution to this is the Lepscomb et al. Paper that I mentioned, where we actually suggest a definition of actionable science focused on the accepted term, where we say that a scientific claim is sufficiently accepted to justify adaptation action, which we define as near-term physical measures and financial investments, when it is supported by multiple consistent, independent lines of high-quality evidence, leading to high or medium confidence as determined by a diverse group of experts in an open, transparent process. This goes to the history of scientific knowledge and the nature of scientific knowledge that Monica contributed a lot of the literature on, as well as an understanding of land ice science and how to, the history that we got from the Decano and Pollard paper, among other things, that came significantly from Bill's work. My contribution was to look at practitioner-oriented reports at a global scale, pictured here, divided into 3 temporal scales, or categories. One is papers that emerged between 2012 and 2015, those that emerged between 2016 and 2020 in red, and then in aquamarine, those that emerged between 2020 and 2024. And you can see, kind of similar to the McInnes et al. Graph, up and down. One level, consistent for a number of years, then up for a number of years, and then down for a number of years. And we found that the reason for this was the appearance of the Decano and Pollard 2016 paper in Nature, which posited marine ice cliff instability. Terrific science. I always am quick to point that out. Important work. And it was, in fact, uptaken, if that's a word, by these practitioner-oriented reports, in many cases written specifically for practitioners doing adaptation planning, in red, where the numbers went up from an average of about 1.4 or 1.5 meters to 3 meters, 2.5 to 3 or more than 3 meters in a few cases. What then happened was the Edwards et al. Paper came out in 2019, revisiting Antarctic ice loss, and kind of undermined some of the conclusions in the Decano and Pollard experimental modeling paper from 2016. Exactly the way science is supposed to work. We're not talking about how science is supposed to work In my talk here, I'm talking about how actionable science is supposed to work. And what happened was all these numbers that were in red, in the red reports came down in the aquamarine reports. And so we were back down to close to where we were prior to the excursion represented by the Decano and Pollard uptake. This is classic whiplash and has led to great confusion in the practitioner community, some frustration, and some difficulties. And I would argue engages some risk of maladaptation as well. The recommendations in the Lipscomb et al. Paper include recommendations for practitioners, recommendations for scientists. I'm not going to read these because we're pretty much out of time, and recommendations for journalists. Think about being cautious is I guess the advice to everybody I would summarize when looking at new science. See it in the perspective, in the development of knowledge in which it actually exists. And in particular for scientists and practitioners, work together across the boundary between science and practice to advance a more holistic view of what we know and what we don't yet know to support adaptation planning and action. My last slide, if you are interested in this work, you are invited to help make progress in it going forward. Peers, the global community of practice that I mentioned, is standing up an actionable science working group. You might consider volunteering for that group. What we're going to do is engage some of the questions involved in the Van der Waal et al. And Lipscomb et al. Papers, which were co-produced scientist practitioner outputs and other viewpoints. And so familiarize yourself with these viewpoints about actionable science, and then think about volunteering for the Actionable Science Working Group, which will consist of scientists and practitioners. We'll have goals of translating today's science and getting into a high-end conversation in a high-end subgroup, which is so important in risk assessment for practitioners, to engage with issues related to Antarctica, Greenland, the ISMIP ensembles, confidence levels, etc. This is the place where we can make progress in correcting the confusion and some of the whiplash that we've seen in the community writ large between scientists and practitioners. And we would invite you to participate in efforts to try to make more sense of that. And to do that, contact me at dbhar@sfwater.org, and I can put you on the list for opportunities to volunteer to make sense of this conversation. Thanks.
Many thanks for this. Do we have any questions?
Hi, David. Thanks. That was a great talk. So I'm just wondering if you can maybe talk about what the low-hanging fruit is to do to kind of improve communication avenues in such a funding-constrained environment where ideally you need some sort of institutional mechanisms to get conversations going, to actually have this kind of translation across the science society boundary. If there's any kind of things that can be easily done in a constrained environment such as the one we currently find ourselves in.
I guess I probably use the term volunteer. I didn't think of it in that terms, but that's where a lot of the progress can be made. Those who are interested in building on the conversations they have in their labs, in conversations with a broader set of society folks. The Peers Actionable Science Working Group is looking for funding now, but we don't need a ton to have these conversations, and we think we can do that coherently by bringing folks together and you know, not spending a lot of money, but spending a lot of time talking to one another and coming up with white papers over time. It's not the only way we're going to do this work. This has to go on in an ongoing way, but we'll hope to do that without gigantic grants coming our way from federal sources.
We have one question online from Robert.
Thank you. I enjoyed that presentation. One thing that strikes me, though, is that in presenting to practitioners, a lot of the challenge arises from the fact that we're looking at very long lead times that confound the scientific uncertainty. Would it be more effective for communicating with practitioners if we, instead of emphasizing the error bars in the amount at a fixed time, but rather the error bars in the arrival time? So, for instance, the Canto and Pollard paper says there's this marine ice cliff instability. We don't know whether or when it will be triggered, but that will be the point at which we start accelerating So we're pushing things backwards and forwards in time for the extreme levels with a specific observable event preceding the high levels by perhaps some decades, at which point I think you're getting closer to something that's more actionable and closer to what actual practitioners are deciding when they're making multi-decadal but not multi-century plans for infrastructure, for instance.
Yeah, absolutely, Robert. That's the way decision making under uncertainty as you kind of get out toward the end of this century and beyond has to occur is with the uncertainty bars and with triggers and thresholds where you identify when events or observations or even new science that is maybe a little stronger and has more strong support for it says that you're 20, 30, 40 years from a certain condition. That's about the large infrastructure time frame, at least in the United States, for building stuff. At the same time, and looking at the time scale. So Decano Pollard 16 said 2100 for significant amount of Mickey. Decano 21 said 2150 for significant amount of Mickey. Both of those papers, in my view, are not actionable because they're not supported by multiple lines of evidence yet. At some point, we may have a multiple line of evidence that talks about Mickey occurring. And I think that if you look at the AR6 outputs, you can see the way the time frame for both medium and high and low confidence science would produce certain changes. And for the most part, some of the big numbers that were in the McInnes chart that I showed are 2300 or 2400 or 2500 sea level rise numbers, global mean sea level rise numbers, which means they're extremely important, particularly on the mitigation front, but on an adaptation front, they're not extremely important at all. They don't figure in, because as you said, we're planning decadally, not in a century by century kind of way. And so I think understanding projections, both in terms of when they're projected to occur for a certain model or what the time frame would be, is all really, really important. But what's most important is I think for us right now, is differentiating between experimental outputs that need more work to become a scientific consensus, and the consensus items that we have before us today that give us plenty of difficult things to work on without the risk of maladaptation that might come from absorbing a new paper that tells us we're looking at 3 meters of sea level rise in 2100 when we're not.
Many thanks. And so we are going to close this part of the session. So a big applause for everyone. And also, thank you for staying a little bit longer here. Okay, see you back at 3:30.
All right. We're going to get started for the second half of our land ice session. And thank you for indulging us with a shorter break. We'll have more time for a break after the session. And our first speaker for this second half is going to be Michele Petrini, who is going to tell us about the coupling into NorESM and with CESM.
Thank you. So yes, I'm gonna just gonna give an update on the work that we've been doing with the NorESM, the Norwegian Earth System Model, and this work is a result of a collaboration which is very valuable for us. So between scientists and software engineers in Norway at the Norwegian Research Center and the Norwegian Meteorological Office, and people here at NCAR. So I'm gonna start with a simple introduction, very general ice sheet coupling in our system models, a bit try to think about the goal, and then I will just go into the specific NorESM, what's new in NorESM 3, so like an overview and some preliminary results, and I will particularly focus on the ocean forcing around and under the Antarctic ice shelves. And I will just conclude with the roadmap towards CMIP 7 and the coupled ESM, ISM, ISMIP 7. So for the ice sheet coupling in global Earth system models, I mean, the why I think is pretty clear. We can assess the impact of processes and feedbacks between ice sheets and climate, atmosphere, and ocean circulation. And we can evaluate feedbacks that are very important for ice sheet loss, like the melt elevation feedback, the ice albedo feedback, and what happens in the ocean when there is melt from Antarctica, for instance. But also because the present and future distribution of glacial meltwater is going to be then consistent in the Earth system model with the climate and the model ice physics, which is very important. And if you don't have an active ice sheet model coupled to an Earth system model, you cannot have that. You always have some kind of approximation or parameterization for the glacial meltwater fluxes. And in a very ideal world where Earth system models are not biased, introducing ice sheet coupling would give you, at the same time, a model that is more useful because you can answer more scientific questions and more realistic as well, because then you have, for instance, maybe a distribution of present-day meltwater fluxes that is realistic. But for the actual real CMIP Earth system models, there is always the need of a compromise between a useful model, so a model setup so that allows you to evaluate the coupled system, and possibly with like a free evolving components, and a model that is also realistic, so that to some extent is matching the present-day climate and the present-day ice sheet extent, basically present-day condition as a baseline for future projection. And then specifically when we think about ice sheets in fully coupled Earth system model, ice sheet model context, there is a number of choices that we have to make. For instance, let the ice sheet extent free evolving or keep it masked to the present day. Do a paleo spin up, like a full paleo spin up, or inverting for basal friction coefficients. And also for the ocean melt parameterization, using tune parameterization or having more complex like plume models or cavity circulation models. These are all choices where that are going to impact the result, of course. And maybe there is no like a right answer, like on a general point of view, but it depends a bit on the application, on what we are going to use the model for. And when I think about more like coupled Earth system models and ice sheet models participating to CMIP, that was a bit my question for Robin Smith before. There is the question of what is the best way to go, because if maybe every model is going to tune to the present day, then this is going to change drastically the response in the CMIP ensemble. So I think it's nice to think about this while we continue on the work. Now coming to NorESM. This is where maybe we left from NorESM 2. So the Norwegian Earth system model is largely based on CESM, and there's a CMIP type model for atmosphere, land, ocean, including the biogeochemistry and sea ice. And in NORISM2, there was an interactive Greenland ice sheet component using the community ice sheet model. And in NORISM2, the coupling included surface mass balance, and there was no ocean forcing involved. And then at the same time, the CESM is giving back to NORISM the ice cover, change ice cover extent, and freshwater fluxes. So that can be seen in the illustration there. And so there are two papers that are in review about NORISM2 coupled with CESM over Greenland. And then now going to NORISM3, what's new? Basically, we're going to have, there is the capability for interactive Greenland and Antarctic ice sheets components. And also now this includes an ocean to ice sheet coupling. So that's the main difference. Then there are some other changes, some maybe minor changes or more technical, that has to do with new ice sheet grids, which are going to be the same as for the ISMEP, and also the slightly different glacial meltwater routing scheme that is going to through Mozart. So it's going to pass through the runoff model. And it is a slightly more efficient way to handle this. Now, for the SMB forcing, not much has changed since our NORISM2 or CESM2. So the SMB is calculated in a land model at multiple elevation classes and using a surface energy balance scheme and accounting for some snow and firm processes. And then there is the downscaling from CLM to CESM. So from about 100 kilometer in a 1 degree simulation to 4 kilometer. And the elevation classes are actually meant to better represent the surface melt at the steep ice sheet margins. And one thing that is going to be important to remember when we see a little bit the SMB over Antarctica is that the melt is downscaled using elevation classes, but the precipitation is not. So there is the downscaling for the surface temperature. We're using a fixed lapse rate of 6 Kelvin per kilometer between each elevation class. And then in each elevation class, there is the energy balance scheme, and the melt is going to be calculated. And then, and then you can see a little bit just an illustration of maybe a large, I don't know, okay, like a 1 degree CLM resolution, and then a 4 kilometer for Greenland, or 8 kilometer for Antarctica, which can have a very different elevation and then can end up in different elevation class bins. Now coming to the ice sheet, oh no, sorry, yes. So these are the first results from a couple NORISM-free CESM tests. And what we can see, I mean, this is done with a climate that is really not in equilibrium. So it's just to get an idea of what we can expect and to see what patterns we have. And for Greenland, we have fairly similar patterns than in NORISM-2. We have a ablation area mostly in the southwest or central west, and definitely less in the southeast, where we see that there is a quite large precipitation, and that has to do with the fact that there is no downscaling with the elevation classes for precipitation. And then on the right, you can see the SMB for Antarctica. And there is essentially no surface melt, just very little, maybe you cannot see it here, but sometimes there is a little at the tip of the Antarctic Peninsula, but for the rest, it's just mostly accumulation at this time. And you can see also that it's going to be a bit challenging because the patterns of precipitation are quite broad, and also the values are a bit overestimated compared to what we know it's happening in Antarctica, which is very dry. So we will need some work to basically reduce a bit the numbers there for accumulation. Now coming to the ice sheet ocean interaction, so ocean forcing. Now there is immediately a challenge because the ocean model component in NORISM does not resolve cavities. So ice shelves are just treated as land. And then we need to do something about this if we want to force our ice shelf with ocean forcing. So what we first do, we take 3D ocean temperature and salinity, far field, so outside basically the land mask in the ocean model, and we remap them from LOM to CESM. And we have 30 layers between subsurface and about 2,000 meters depth. And you can see what happens in just an idealized illustration in this first step, that we end up in our like a CESM grid but we have basically missing values under the cavities because the ocean model doesn't see that. So what we need then is to extrapolate these values under the ice shelves. And for now, we are using an extrapolation algorithm that is filling the cavities with multi-layer ocean thermal forcing, which is the difference between the ocean forcing at a given depth and the freezing temperature of the ocean water given a certain salinity and depth. And this is an algorithm that is based on work that Bill Lipscomb did, and now this is accounting for bathymetric obstacles. So basically, if there are some seals in the bathymetry, the water cannot penetrate deeper than that. I mean, water will see the blocking of the bathymetry. And there is also some smoothing based on Gaussian filtering. So you can see now in a plot on the left, basically we're trying to map the depth at which the water outside the cavities is entering the cavity. So basically, this is not ocean temperature, but this is a far field water depth. And we're doing this just to basically try to keep track of what the algorithm is doing. And because we want to check in the first place that we have like deeper water entering like the deeper part of the cavity. And you can see, for instance, if you look at the filch run, we can see how deeper water is entering the Filchner cavity, which is typically deeper. And also you can see a little bit the pattern of the lower ice surface. We are somehow pleased with that, with the pattern that we see. And on the right, you can see a transect of the Emery shelf. We have an ice shelf here on the top left, and we have the bedrock on the bottom right. And you can see, again, this is a map of not temperature, but just the depth of the origin water that enters the cavity. And you can see how this is basically the limit, and water deeper than this will not enter and is going to fill the cavity. There is also here some lateral circulation, but in principle, we see that. And then we repeat the experiment, basically adding like one big seal at the entrance of the cavity, and you can see how that now the red color, the red water cannot penetrate anymore, and then we have a shallower water entering the cavities and filling the cavity. This is somehow like a first way to see how our algorithm is doing and how this works. Now we can have a look at some basal melt value. So we are using this ocean forcing, thermal forcing, in Antarctica to calculate the subshelf melting using ISMIP6 parameterizations. We have on the left the local, no-local parameterization, and on the right the same parameterization with the slope factor correction. And this is just like published ISMIP6 parameterization. Just to get you an idea of the patterns that we see. In general, we have quite a lot of melt in West Antarctica, but also a little bit in this part here, very little melt in the Filch Run, and a little bit more melt in the Ross Shelf. And again, this is based on an ocean that is really not close to equilibrium, so it's just a little bit to check what values we can expect at the moment. And there is going to be, for sure, a lot of need for calibration and bias correction probably for NORISM ocean. For Greenland, we also want to include some ocean forcing. That's the plan. And now Heiko Gulzer, my colleague, is working on a new parameterization to be included in CESM and to be used for fully coupled simulations. This is a map now that is showing the distribution of freshwater fluxes from the ice sheets. So we have basically we have on the left frozen runoff and on the right liquid runoff. So basically on the left is iceberg calving, and on the right we have subshelf melting because there is no surface runoff. So it's all basal melt. And you can see basically how especially for the basal melt, this is showing where there is more melt mostly in the western part of Antarctica. And then we are also a bit surprised to see a lot of melt here in Filch Run, considering that there is not a lot of melt, but on the other hand, the area is large. And the meltwater is added at the closest ocean point, and so that's why there is more melt. There is like a large signature of melt there. And at the moment, these fluxes are all added at the surface. And we would like to do some work to include these fluxes also at a given depth, but this is going to come like later in the development, and very likely not for the next round of CMIP or ISMIP. Now I want just to focus shortly on ocean forcing. So we just took basically NORISM2 output, and we used the extrapolation algorithm to see what values we get in the ice shelf cavities, to see a little bit how this water is entering the cavities, and just have an assessment of this algorithm, on how this algorithm work, and also how biased how large is the bias in NORISM2. In this setup, the ocean model is just kept in data mode, and the ice sheet is not evolving. So this is a purely diagnostic step. I'm a bit late on time. Okay, I'm just going to show it for the raw shelf. We have, again, on the left top, the ice shelf, and then the bedrock. And this is the direction of the extrapolation. So the water is entering this way. And we have here the PI control, here the difference between PI control and the World Ocean Atlas, which of course doesn't enter in the cavity. And then we have like a high warming scenario on the right. And we can see how basically in a high warming scenario, the whole water and whole cavity is warming up. And, but we also know that we have very large bias compared to the World Ocean Atlas. So this is just a preparation to basically reassess the ocean in NORISM3. But it's also an example on how this extrapolation scheme work. I'm going to skip, this other ice shelf, but I have lots of transects if you're interested in this. And I'm just going to conclude with a very schematic roadmap. We are now, at the moment, running a NORISM3 climate-only spin-up. And when we get as somehow close to equilibrium, we would like to force offline first the Greenland ice sheet and the Antarctic ice sheet to basically do an offline spin-up, which is going to be done probably with an inversion. And then we will need to calibrate the ocean melt, and from there we can basically start to turn on the ice sheets. For CMIP 7, the plan is to run with a Greenland coupled, possibly with some ocean forcing, but Antarctica is going to remain fixed because it's really too early for this. But then we would like to have both Greenland and Antarctica for the coupled ISMIP 7 that Robin illustrated. So that's a little bit the plan. I don't include the time because it's already stressful enough, and I just conclude here.
Very cool presentation. I have more of a question regarding the surface mass balance forcing that you used for CESM. Did you account for snow and firn processes for surface mass balance within CESM, or was it just in NORISM? Oh, within CLM. Okay.
But also CSM, yeah. And that's totally inherited from NORISM2 or CSM2.
Now, Ishrak, since you're up, why don't you come over here since you're the next speaker, and Ishrak Feroz is going to tell us about his using CESM to represent blue ice in Antarctica.
Okay, so I'm Feroz Ishrak. I'm currently a visitor within CGD and part of the UCAR Next Generation Fellowship, and I'm going to present some plans and updates for my work within the Land Ice Working Group and how CESM can help us better drill for oldest ice in Antarctica. I'm an ice core scientist and a paleoclimatologist by training, so any story I tell about my science involves past climate records. So this is kind of the standard plot that a lot of us in our group use. It kind of shows how the different paleoclimatic records that we have of Earth span over time. So on top we have the ice core records for the top two plots, and then in the bottom we have the benthic stack record of surface temperatures on Earth over the last 5 million years. And we care about filling the gaps that exist in the ice core record, particularly because ice cores are fantastic climate archives. They're not just sedimentary archives of information of Earth's history. They also pretty pristinely store the historical geochemistry of Earth's atmosphere, as well as surface transport of impurities in the past. And so generally what happens is what we want is the oldest and the longest continuous ice core we can find, and often those locations end up being in Antarctica, especially in the eastern Antarctic plateau in the interior of the continent, where we end up finding ice cores as old as currently from beyond Epica in Europe, 1.2 million years. But there's another location we can look for to find oldest ice in Antarctica, and they're not even close to the deepest parts of the ice sheet. These are called blue ice areas, where solid ice itself is exposed on the surface of the ice sheet. So this is a map on the right of different exposed blue ice areas across Antarctica. So it's a little bit hard to see, but the dark blue patches are these blue ice areas where a combination of bedrock topography and ablation outpacing accumulation in these locations preserve old ice, ice as old as 6.7 million years old. So this number is actually quite recent. It's from last week. We drilled this ice core last field season, and we just got the oldest ice age for this core. And currently, this is the oldest piece of ice core record we know exists on Earth. But the problem with blue ice areas is that we don't understand why they exist and why they store ice nearly as old as this. So the blue ice area that we've been drilling in is Allen Hills. It's outlined in red. It's pretty close to the US Antarctic base at McMurdo, but there's blue ice areas everywhere. And the finding of the 6.7 million year old ice in Allen Hills raises some questions about blue ice areas, and these are the kind of the questions I'm asking as part of my dissertation. What factors in the Antarctic ice sheet contributes to such old ice preservations in these marginal locations? Do all blue ice areas in Antarctica have the potential to preserve ice core records this old, almost 7 million years old, or does it vary from where you are in the continent? Can we systematically identify such old ice drilling sites in Antarctica, both in blue ice areas, and I'm going to keep calling them BIAs from now on, and the interior of the continent? And we plan to use the CESM to try to investigate these questions, because CESM as a model is pretty uniquely situated in terms of its capabilities for us to be able to ask these questions. So obviously, to ask about ice this old, we need to be able to simulate the ice sheet for just as long of a period of time. And as you've seen in the previous presentation by Dr. Petrini, climate forcing and forcing ice sheet models is a pretty complicated question. And it becomes even more complicated when you're trying to force an ice sheet for as long as 1 million, if not 2 million years in the past. To simplify this process, we're going within CESM, we're implementing a climate index method that was originally implemented by Johannes Sutter et al. In 2021. We essentially take the Epica Dome C record. So we essentially take the Epica Dome C record over here and then paste it onto the marine benthic stack to create this long-term record of temperature near Epica Dome C in Antarctica. And we normalize this temperature field to create this normalized index called the climate index. And obviously this varies over glacial and interglacial timescales. So the largest climate index value happens in the last interglacial, while the smallest climate index value happens in the last glacial maximum, and present day is roughly around at 0.7. So in order to force the Antarctic ice sheet, we need temperature fields and precipitation fields. And we essentially use this time series to generate these temperature and precipitation fields at 100-year intervals for as far as this record goes. We take the present day temperature and then add a perturbation based on where we are in this time series. If we're in the blue section of the time series, we perturb using a temperature field from the last glacial maximum reconstruction from the ICESM. And if we're in the red part of the time series, we perturb present-day temperature fields using the last interglacial part of the temperature field from CESM. And we're weighing these perturbations with this weight, which is essentially a normalized value of how far apart, at a given point in time, how far apart the climate index values of the point in time, the climatology at that time is from the climate index value of present day, because we're perturbing the present day climatology. What it essentially lets us do is we're basically interpolating between the present day and the last interglacial, or the present day or the last glacial maximum, to create these generative temperature fields, and then we use these temperature fields to essentially scale out using a scaling relationship, a precipitation field using this equation below. And this essentially will let us not only spin up our model on a accurate paleoclimatic timescale, but also let us better use CESM to understand how ice transports over glacial interglacial timescales. We're just starting in this procedure, so we're writing this capability into CESM to generate these temperature and precipitation fields as the model runs over time. But before we're testing that forced run out, we were doing some preliminary spin-up runs using just present-day climatology from ISMIP 6. The preliminary spin-up run I did for 12,000 years at 8-kilometer resolution and 41 vertical signal levels, so fractional levels at a given depth. We run for 12,000 years under current constant climatology, time step at 2 months, and the age is treated as a tracer in CESM, and the tracer transport is done using an incremental remapping scheme instead of a Lagrangian scheme. This incremental remapping scheme is a unique capability with CESM that makes it very lucrative for these experiments for ice core science. Because it's second order stable and it's not too computationally expensive. Some of our results are from the spin-up run are here. So this is a involved plot, so we'll walk through it a little bit slowly. So on the left, you're seeing the age of the tracer, ice age tracer, at 9% of depth from the top. So this depth can vary depending on how thick the ice column is at a location, right? So we're seeing that the ice is very young near the periphery and the ice is very old near the center. And we have this vertical line crossing through the map that creates this cross-section on the right. And the cross-section, you can kind of immediately see something's wrong. This is not what we expect from an ice sheet. There's a big chunk of the ice that's 12,000 years old. That's not something that happens on an ice sheet on a regular basis, and that's something we expect. We started off this entire modern Antarctic ice sheet from time step 0, and we ran it only for 12,000 years, which is not enough time for all of the ice that started at time step 0 to melt away. Generally, ice takes around 800,000 years to melt out at the bottom, and kind of all of the ice that exists in the in Antarctic ice sheet will be replaced by new precipitation. So what the transport and the new ice is shown in this thin band of ages that you see on the top of the ice sheet. And this thin band isn't physically consistent, but it can still give us some qualitative insights about what blue ice areas are. if you notice this circled section, so the corresponding section in Antarctica is also shown, the younger thin section of the transported new precipitated ice and snow is much thinner there than most other places in that slice of the ice sheet. And that's primarily due to the basal topography and how the ice is being transported over these ridges on the bedrock. But it's also the location of where Allen Hills is. So it immediately shows us something that's physically consistent of older ice. So in this case, our old ancient ice is what we started with from 12,000 years ago. Old ice being pretty close to the surface in blue ice locations where blue ice areas are compared to everywhere else in most other places in the ice sheet. This somewhat tracks with what we observe in Allen Hills. In Allen Hills, the surface of the exposed ice, the ice just on the surface is around 100,000 years old. There is no new precipitation, new snowfall there. The same thing we can see on a horizontal cross-section across Antarctica. And now on this horizontal cross-section, you can also see a distribution in the band of ages. If you look at the circled region, there's a really thinned section of this young age band of the ice, and that corresponds to another blue ice area. It's another blue ice area in this location. It's called the Prince Charles Mountain Blue Ice Area. These are very well surveyed blue ice areas because it's also a treasure trove of meteorites that gets scattered all across these locations. So this indicates to us qualitatively that we're probably at this resolution starting to resolve some of the processes that result in blue ice areas in Antarctica. Another thing I wanted to show you is just the spatial distribution of these age tracers at the original map that we've been studying for the last few minutes. If you look at the bottom left, it's the Victoria Land blue ice areas, which is the most well-studied blue ice areas in Antarctica, which is where we do field work in Allen Hills. And the known present blue ice areas are marked in blue. I know it's a little bit of a visibility issue, but I couldn't not mark them in blue. But a lot of these age structures, so the distribution of ages on this depth on the ice sheet, follow pretty closely with where the distribution of current blue ice areas are. And that is not something I had expected from my understanding of blue ice areas, because so much of blue ice areas are motivated or run by the climatology and the changing high ablation regions in Antarctica. This is almost completely modulated by the basal topography here. So in conclusion, work is underway in developing the paleoforcing scheme for CESM that enables this ice sheet evolution over time, much larger timescales. We did a 12,000-year spin-up run using ISMIP's 6 present-day climatology. Longer model runs are needed for age tracers to become truly useful, because we don't want that giant chunk of ice that's 12,000 years old and not physically consistent with our observations. We want to compare limited Lagrangian age tracer transport with our current age tracer transport scheme to see what the differences in their capabilities are. And our initial spin-up experiments with age tracers are qualitatively reaffirming the usefulness of high-resolution CESM runs to better understand these old ice preservation of blue ice areas, but also confirming some of these observational assumptions we had for decades about blue ice areas in a more consistent physical modeling sense. I want to thank my advisors, Bill Lipscomb and Dan Amron, and I also want to thank Gunter Legee for their guidance through this process so far. And I also want to thank the UCAR NextGen Fellowship for giving me the chance and the resources to be able to do this really fun work with ice sheet model. Thank you, and I'll take any questions.
For one question.
Thanks, Ishak. It's really cool to see this. I was wondering, in the model and in real life, do you expect that the blue ice areas are where the ice is preserved or where it is exposed? And to what extent do you think it's transported from other places and could bear the signature of that transport?
I because blue ice areas obviously have this very stratigraphically consistent surface unit of ice that's still really old, around 300 to 400,000 years old, but then it also has a disjointed basal unit that's 6 to 7 million years old. And we don't expect ice that old to have kind of lasted in these marginal locations, especially in some blue ice areas where the ice flow is pretty consistent and fast near the bottom. So from my intuition, from my understanding, it's probably a combination of both, but both two different processes resulting in two different archives, I believe.
So I noticed a lot of your regions are near the coastal areas, and I'm wondering if GIA would have any impact on these runs over the long term.
Wait, could you say that again, please?
So I'm curious about the impact of glacial isostatic adjustment on this sort of simulation in the long term.
I think that it's important to consider because, especially in the long term, in Allen Hills, there's evidence of the ice sheet to have been almost twice as thick than it is now. So it is going to be an important aspect of trying to model the ice sheet in such a high resolution in the long term, because we're looking at very strong changes in ice sheet elevation in these locations, and I don't think the glaciatic adjustment aspect of that would be as negligible as it is a pretty controlled experiment as this spin up.
Moving to our next speaker, Miriam Viscano, she's going to tell us about elevation. Oops, read a little bit, but about Greenland and mass balance rate changes impact on Greenland.
Okay, thank you very much. Okay, so yeah, most of the projections that we have from the ice sheets are based on ice sheet models that are forced with the output of climate models. CESM2 was contributing to the last IPCC report with a couple assessment, so climate and ice sheet coupled for Greenland. And hopefully we will have more of these couple models for ISMIP 7 or for the next IPCC report. Okay, so this cartoon is summarizing the coupling, so changes in the topography of the ice sheet are passed to CAM and also to CLM, and then changes in the freshwater fluxes are passed from CLM to the ocean in the case of surface runoff, and from CISM to the ocean in the case of ice discharge, so the solid input to the ocean from the ice sheet. Okay, so the model has a very relatively realistic surface mass balance calculation. So with an advanced scheme for snow and fern. And we have published the evolution of the ice sheet up to year 350 under a 1% to 4 times CO2 scenario. And here, what I'm going to present is a comparison of an extension of that simulation to year 500 with a one-way couple simulation. So in the one-way couple simulation, the topography and the meltwater are prescribed as in pre-industrial simulation. So they are not evolving in time as seen by the climate model, but the ice model is running, receiving the change in climate from CESM, and so it is change in topography. Okay, so first you have here the time series of what is going on. So the CO2 is increasing up to year 140, and then we are reaching 4 times CO2. That is more or less the CO2 corresponding to year 2100 under SSP 58.5. And after that, we keep CO2 constant. You can see global warming in the panel B. And the red and blue lines correspond to two-way and one-way coupled. If you look at the NAMOC index, so the maximum of the overturning, the two lines are very, very similar, which rules out a meaningful contribution to the weakening from the Greenland ice sheet. And then I have several plots here that are showing the evolution of a number of diagnostics in the ice sheet model in the two simulations. So if you look at panel E, you have a cross there. So at year 280, we have a separation of the cumulative sea level rise. And similarly to other models with a lower resolution, run one-way coupled and two-way coupled. The one-way coupled run overestimates the mass loss. The difference is not very big, which we will see speaks highly of the downscaling protocol within CESM that can correct for a large part of the elevation change. Okay. This is the output from CLM. So we can compare the melt in the one-way simulation with two-way. So this is change referred to pre-industrial. And you can see that the melt is much higher in the two-way simulation as the topography is going down because of the elevation feedback. And you can see the difference. Now what we are going to do is we are going to look at year 500 again. And we are going to divide the change in elevation. No, sorry. The change in near surface temperature in the two simulations, two-way minus one-way, by the change in elevation. So we are trying to map here. We are trying to isolate the change in temperature that is due to the interactive coupling, okay? So you can see here units of Kelvin per kilometer. And we see very different magnitude for winter and summer. So, and you can see month by month ice sheet average, how the so-called lapse rate, so the difference in temperature that comes from the difference in elevation is much higher during the winter than it is in the summer. And we are proposing that a large part of this overestimation of mass loss in uncoupled versus coupled runs is due to factoring or correcting this climate by a standard lapse rate of 6 Kelvin per kilometer, while what we are seeing here is around 2 Kelvin or 3 Kelvin in the summer. However, well, in our model, these differences are heavily corrected by the downscaling procedure that involves recalculation of the surface fluxes at the different elevation classes and so on. So our model CESM is accommodating much of these different lapse rate in the uncoupled versus coupled cases, but maybe in other models like PDDs or other approaches to calculate the melt can make a big influence whether you are taking a lapse rate of 6 Kelvin per kilometer or another lapse rate. Okay, so here we are looking at one location in southern Greenland, and we are looking at the evolution of the elevation. It's fixed in the one-way run, obviously. We are at 2,500 meters. You can see how the melt by year 500 is double in one-way, in two-way coupled. And if we are correcting temperature, so we see the lines of the evolution of temperature in both runs, and if we are correcting with 6 Kelvin per kilometer, we have this dashed line that is way more than what we have in the two-way reference coupled case. Okay. For long-wave radiation, we also see that this lapse rate, so how the long-wave incoming is increasing with a decrease in elevation is much less in the summer than it is in the winter. So, we are looking also at blocking, and we see that with a decrease in topography, the blocking is reduced. And this has effects on the surface mass balance because the blocking enhances increases melt. And now I'm going to move to a different experiment. So we continue with reference as the two-way coupled, 4 times CO2. That is the red line. And now we are going to look at a green line where we have a period of very intense mitigation. So we are going down in CO2 from 4 times CO2 to 1 time CO2, so pre-industrial, very, very quickly. And then we look at what happens with the climate and the melt over Greenland. And for the global temperature, we see a very rapid reduction, and there is a revamp that is connected with an overshoot in the ocean circulation, so you can see it in the panel C. The mass balance for the red line is going down from a mass loss of 8 millimeters sea level rise per year to 0. So by reestablishing pre-industrial CO2, we stop the mass loss, so the mass balance is 0 approximately. We don't regrow the ice sheet. And we are gonna see that what is going on here is that we have a residual 2 Kelvin of global warming in the simulation, which makes the melt relatively high compared with pre-industrial, but at the same time, the ice sheet has lost sufficient mass and retreated, such as the ice discharge became 0. So now a surface mass balance of 0 results in a mass balance of 0. So here you have the maps of warming compared to pre-industrial by year 300. And then we have the mitigation. We have some residual warming. And that increases a little bit with the overshoot of the NAMOC. Okay. If we are looking carefully at the firn and the snow conditions, we can track how the the surface albedo is evolving and how it responds to the mitigation. And we can track also the refreezing. We can track also the evolution of particular surface mass balance components like the snowfall. And we can also track how different components of the melt energy are evolving and responding to this mitigation. If you look at the green line, you can see the net solar radiation, and you can see how it follows or correlates very well with the total melt because of the albedo feedback. So it's following, so this amount of melt and the albedo are extremely coupled with each other. So then you see the similar evolution. And yeah, see a reduction of any component like the latent heat flux, the sensible heat flux, and the net long wave. Okay, so the conclusion is that here is that the calculation of the ice mass loss as given by the CESM is similar in both runs, one-way and two-way, until year 280, because we have similar AMOC strength, we have similar Arctic climate change, and we have elevation corrections in the surface mass balance calculation that are accommodating up to year 280 the differences. And then, yeah, then we see this overestimation in the one-way coupled case. And then, yeah, reducing CO2 to pre-industrial levels after year 350 is resulting in zero contribution to sea level rise from that time. And it will be very interesting to repeat this mitigation with not so aggressive mitigation, earlier mitigation, and so on, and see how the ice responds, because there is some delayed responses that are very interesting. There is a lot of memory in the snow and firm conditions.
Not sure we had the discussion already, but I was curious about when you calculate the lapse rate is based on the difference, right? And the temperature, is it seeing the effect of melting the ice? Or is it temperature that comes from the atmosphere and has not went through the ice melt? If that is clear. Yeah.
What we are plotting here are cells that have a change of more than 250 meters, okay? And we are comparing the two runs. And because you have the same CO2 forcing in both, you assume that the near surface temperature change is only because of elevation change.
No, that I completely agree. My question was, so there is going to be some ice melt, and so the air temperature in the summer is going to lose some energy to melt the ice. And so I'm wondering if the lapse rate is so low in the summer because there is a little bit of loss of energy because of the melt.
Yeah. So this is the process that is underneath. So if you are looking, for instance, to you look at the IPCC Interactive Atlas, and you look at the Arctic in the summer, and you look at the Arctic in the winter, you see that there are relatively small changes in near surface temperature in the summer, and this is because the energy is going to the melt. So this is the story that is going on here. Yeah.
All right, thanks. Our next speaker is Zeki Yin, and he is going to tell us about Greenland emulation.
Hi everyone, my name is Ziki Yin. I'm a PhD student from CU Boulder, working with Anish Subramanian, and today I'm going to present some early results for my last PhD project. And yeah, so as we know, the Greenland ice surface melt is driven by complex mechanisms involving both local impact and also remote processes. And most, like CSM2, there are still many CMA6 models that lay realistic surface melt calculation over Greenland ice sheets. So machine learning methods provides, trained with CSM2 data, provides a way to emulate surface melt and then apply this emulator to the other CMA6 models, and also can help with the interpretability about the driving mechanisms of surface melt. And for example, this is an example by Silverwood et al. 2021. And they, in this work, they build they use neural network to build an emulator, the integrated surface melt from the Greenland ice sheet, and also use the error weight to explain the driving mechanisms of atmospheric pattern. This project, we are trying to go one step further to build a emulate 2D surface melt field. And the method we are using is a graph neural network. It's a machine learning method that learn from data structured as graphs by passing meshes between neighboring nodes. And this kind of graph neural network has been successfully applied in machine learning-based weather prediction models like the Google's GraphCast. And compared to another commonly used machine learning method named convolutional neural network, this graph neural network is more flexible and can operate on unstructured grid. So it will be easier to transfer the emulator to other models later. And based on the graph neural net, we borrowed the idea from transformer to add another layer of global attention. So in this way, the method combines local message passing from from the neighboring nodes, and also long-term impacts from all the other nodes. And compared to a pure transformer model, this model, graph transformer, also integrates the graph structure into the attention mechanism. So this is also important for geoscience study. And such modeling structure has been applied in the, for example, AI forecast system of the ESMWF. The data we are going to we are using is from the historical CMF6 simulation from CSM2, which has 11 members. And we are using the 10 members for training and the last member for evaluation. And it covers the period from 1850 to 2014. Input variables we are using include 11 variables that we think covering the atmospheric impact on surface melt. So including incoming shortwave long-wave radiation, 2-meter temperature, specific humidity, wind speed, snow, rain, and also surface pressure and droplet height to represent the impact of large-scale circulation, and also liquid water pass to represent the effect of cloud, and integrated water vapor to account for the impact from moisture transport from lower elevations. And for this atmosphere variable, we use the JJA mean of these variables. And for output variable, we use annual surface melt. And in comparison, we also tested with JJA mean melt. The figure here shows the region that we extract the atmospheric variables. So we select the region because it includes the Greenland blocking region, and also it accounts for North Atlantic, where the moisture sources mainly come from. Here shows the emulator structure. Basically, it input the atmospheric variables and also use the lat-long coordinates as a positional encoding, and output surface melt at the same year. And we are using different layers of this graph transformer model. So for GNN, specific method called gated GCN, and for the global attention, we use this performer model, which is a variation of transformer that use linear attention, so it's more like less computationally expensive and can scalable to a large data set. The table here just shows some other important parameters of this emulator. And for loss function, we are using a weighted mean square error over the S sheet for our loss. This figure shows the curve of the training loss, and basically, and for different sightings of the emulator. And I have been run these cases just using my laptop, and it takes 5 to 10 minutes to finish epoch. And when I add global attention, it takes up to 30 minutes for each epoch. And for this global attention case, I just run it to 80. After running this, I just save the model and training weight at from the last epoch. And currently, I'm transferring this to GPUs for acceleration. The evaluation metrics of this emulator. So at the bottom, at the second table shows the emulator annual melt. And in comparison, in the first table, it shows the results from the emulator emulating JJA surface melt. And by comparing these two tables, we can tell that it's more challenging to emulate annual melt based on JJA atmospheric fields. And this is understandable because the JJA field may be hard to represent the driving mechanisms in the shouldering seasons. And also, if we're comparing this like 5 variable case to 11 variable, I forgot to mention that the 5 variable case is that I selected 5 variables, all of these 11 variables as a version using only this incoming shortwave radiation, temperature, potential height, snow, and liquid water pass, which is similar to the variables used in the Silverwatt paper. So if we're comparing this, like increasing from 5 variable to 11 variable, we can see that it doesn't necessarily use the RMSE or BES. So it tells us that some variables are redundant and can be removed. Also, like increasing from 2 layers to 4 layers doesn't necessarily improve the result. So there are some testing of the emulator. We can see that adding a global attention slightly decreased the RMSE for both two tables, and also it increased the R square, which is promising. Because actually the results currently doesn't differ very much, so I will mainly show the results from this 5 variable case with a lower mean basis. And the left figure shows the scatter relationship between the true melt and prediction melt for all of the grade. And right, this 2 map shows the mean RMSE and mean BES average over the whole historical period. We can tell there are still large RMSE and BES over these marginal regions, which can be as high as like BES is as high as 100 millimeter per year. And we can also look at 1 year. For example, this is 1990, before the accelerated warming happens. And these 4 panels shows the true melt from CSM2 and prediction, also the percentage of the difference. So we can see the emulator generally captures the spatial pattern of surface melt, but it underestimates the high melt values over the marginal regions, which can be like 20 to 24%, 25% among these lower elevation regions. And also show another case of 2014. We can see there's an increase of the gases, and this can be tell more clearly from this integrated melt time series. Here we can see the emulator doesn't really get the accelerated melt due to warming after 1990s. This could be due to because this increased melt only represent a small amount of data in the training set. So maybe including more SSP scenario could improve this. And one problem we see is the emulator doesn't really capture the interannual variability very well. We see the R is 0.3 is very low. And in the bracket, the number is the R value for in the detrended data set, time series, and goes to 0. Here also, I show this result from the case with global attention. We can see the good news is that after adding global attention, the emulator can get the accelerated melt much better than the case before. But this also results in some overestimation of surface melt in the 19th and 20th century. So to wrap up, the main takeaways so far is that the GAN-based emulator produce reasonable JJA, or I forgot to change it, and also annual surface melt field. But there are still a lot of improvement needed, and especially over the lower elevation. So for next steps to further improve this emulator, we plan to incorporate also the SSP simulations in our training data set, and also continue to perform sensitivity experiment to assess the different like input variables and modeling choices. And for example, we thought about adding surface variables from the land component. And after that, we will conduct feature distribution analysis to connect it atmospheric pattern with the surface melt, and then apply this trained emulator to the other CMA6 models to get an ensemble estimate. And also, by using this emulator, there's also a potential to do probabilistic prediction by if trained with, for example, Gaussian laws, and then we can predict not only the mean surface melt, but also a certain range of melt. Yeah. Thank you. These are the references, and I'm happy to answer any questions.
We have time for questions. Go ahead, Rachel.
You mentioned that it might be missing some processes during the JJA season. Do you have any idea about what those are, or even in the marginal regions?
I'm thinking about spring melt, like in May, for the processes, is more at the low resolution where melt happens early than higher elevations, and this is could be related to air intrusion into the ice sheet, and this is I think it's more when we to predict future scenarios that have more longer melting season in the shouldering seasons.
Let's move on. Well, Rachel, you next. So Rachel Middleton, she's going to tell us about supraglacial water signature in ice sheet.
Hello, my name is Rachel Middleton. I'm a PhD student at the University of Colorado Boulder in the Geomathematics Remote Sensing and Cryospheric Laboratory. My co-authors today are Dr. Uta Hertzfeld, my advisor, and Dr. Tom Tranto. And I'll talk a little bit today about how superglacial water signatures reflect changes in the dynamics of a surge-type glacier in Svalbard. I need this. So the Negerbrand Glacier System is a system of glaciers in the Arctic archipelago of Svalbard, and it consists of a main body, the Negerbrand Glacier, and several confluent glaciers, which are non-surging. And Negerbrand is currently experiencing a surge which began in 2016. I choose to analyze Negerbrand in 3 separate regions. The Upper Crevasse Province, which is in red, the Middle Crevasse Province in green, and the Lower or Chaotic Crevasse Province in orange. And surging is essentially a mechanism that a glacier can experience after a long period of quiescence when the glacier is moving very slow, and it accelerates to 10 to 200 times its quiescent velocity. For example, Negerbrand reached 22 meters per day in 2017, which is about 200 times its quiescent velocity. During this phase of quiescence, the glacier prepares itself for the surge by accumulating a thickness of mass in a reservoir area, or a thickness of ice in the reservoir area. And once this exceeds a threshold, the glacier will surge. And the rapid motion of the surge changes the drainage system, the water drainage system, and its efficiency, which was observed by Barclay Clam in 1987 on Alaskan glaciers, and there's many other field observations of this. We noted that this is not just a switch from a normally efficient drainage system to an inefficient drainage system, but rather a transition. So subglacial water is important to also consider in this process because it drives one of the 2 mechanisms for glacial movement, which is basal sliding. And I've largely been able to learn about this by working a little bit with Bill on implementing some type of basal hydrological model into CESM last summer. So maybe that will eventually come out. But anyway, it was a great learning experience. And typically in Earth system models or ice sheet models, this inefficiency of the drainage system is represented through a general power friction law in which the basal shear stress, represented here in this, just an example of one of these equations, is modified by a friction coefficient that's dependent on the effective pressure and also the basal velocity, where the effective pressure is essentially the difference between the ice overburden pressure and the basal water pressure. But in order to understand how this effective pressure can change at the base, we have to consider how water pressure can even begin to build at the base of the glacier, which means that we need to require an inefficient drainage system for this water storage to begin. And I wanted to see with observations how superglacial water, or water on top of the glacier, might reflect some of these theories or change it. So my main approach was a spectral classification using worldview imagery. And worldview imagery is high enough resolved that it has several pixels inside of each water feature, which could be a melt pond, which is displayed in the lower image, or water and crevasses, which are also there in the lower image. And its apparent low reflectance in the red band in combination with its apparent high reflectance in something I calculate called the normalized difference water index is essentially used with the thresholding approach to identify these small, very small water features. But there is work being done in our lab using a neural network structure called GeoClass by a recently graduated student, Silas Twickler, and Uta as well, to maybe more automatically identify structures in the ice surface, which could include water features. It's also important to collect morphological information and depth information from like ISAT-2 LiDAR or altimetry over the glacier surface to be able to maybe approximate a volume of water. And this is especially important for water-rich regions where a volumetric analysis would also contribute to reflecting how the dynamics have changed rather than just looking at the spatial distribution of water itself. So Negerveen last surged in 1935 and 36, which is approximately 80 years before the beginning of its current surge, which it's still experiencing. And in its pre-surge state, there was limited connectivity to the bed, as evident in these worldview images here, where there was primarily melt streams and a little bit of ponding in the upper crevasse region. And there was some seasonal acceleration, which might indicate still like a little bit of limited connectivity to the bed, but not much. So in the beginning of the surge, during the peak surge state, Negerveen accelerated to 22 meters today, as I mentioned before. And this occurred between 2016 and 2017, when the kinematic surge wave propagated from the front of the glacier all the way to the back of the glacier up into that upper crevasse region. And water ponding doesn't occur during this time. Oh no, you actually can't see, as is evident here, but you can't see them very well. Anyway, there's no water there. But water ponding does begin to occur after this main propagation of the kinematic surge wave, starting in 2018. And then as the years go on, this ponding becomes more extensive. And this is most evident in the upper crevasse region, upstream of where this propagation of the surge wave occurred. And then following in the mature surge state, where the glacier is still at high speeds, but much lower speeds than that peak phase, so like 5 meters per day in the case of Negerveen, I saw these smaller marginal acceleration features, and then like sort of a 1-year delay in when water crevassing or water ponding in the crevasse regions of these marginal acceleration areas began to occur, which is interesting that there's sort of a 1-year lag, and it at least warrants future exploration of the relationship between the surface acceleration, the basal sliding, and the superglacial water connection. But it's interesting at least that the ponding generally tends to agree with the areas of these marginal accelerations. And then a similar process occurs the next year when an acceleration occurs in the upper margin of Negerveen, and we see more extensive ponding, again in those margins, especially the upper margin, from the worldview imagery. So for my future work and some conclusions I want to make, it's evident that superglacial water ponding is a response and not just an indicator of basal sliding, and a response to changes in that inefficiency of the drainage system. It's also evident that the changes are very heterogeneous, and the inefficiency of the drainage system itself is heterogeneous, so definitely reflecting that it's not just a switch from an efficient drainage system with channels and lots of water leaving to an inefficient drainage system everywhere, but ponding can occur upstream of where the inefficiencies are occurring, and it may also occur in those margins semi-locally. But by using both of these lines of evidence, we can work to develop a more extensive theory about what's going on with the drainage system, and then combine this with modeling to make logical conclusions. So there's many questions I want to ask in the future, and I can take questions now.
Questions for Rachel? Yeah.
Thanks, Rachel. Very cool talk. For the ponding features, are you able to use ISAT tracks to estimate volumes of ponding? And if so, or if you want to do that, do you suspect or do you see any patterns in what the amount of ponding is in different parts of the surging glacier?
Yeah, so I have like a working method for estimating the volume, but like the coverage of ISET2 isn't complete over the glacier. There's distances between the tracks, so it requires first using really high resolution surface heights derived from that data, which I use the DDA ice algorithm for, and then it requires calculating the depth from those heights. So I have to go ahead and label all like the local minima and local maxima, and then infer depth from that. And then I have to essentially just make a morphological assumption about the crevasse shape, which isn't super complicated, and I think it's like a good starting point. And from there, yeah, we can infer volume. As far as like relationships between the, say like more ponding in the upper crevasse region or in the marginal regions, I think right now it seems for this glacier system, it's really preferential to how much surface area is covered by those features. And also it would definitely be really sensitive to whatever interpolation scheme I'm using. So it would, I don't think I can answer your question yet, yeah. Mm-hmm.
Any other questions? All right. Well, thank you, Rachel. And we're going to move to our last topic of the session. Summer Minaya is going to tell us more about mountain glaciers in CESM.
How does this work? Good evening, everyone. We're already out of time, but I'll be quick. So I'm going to introduce our work that we have been doing on glaciers, some recent developments, and also towards the end, some science applications of this new effort that we are putting in. So first, I want to start by introducing the different types of glaciers that we are dealing with. So on the left side here, I'm showing polar glaciers. These are on the peripheries of the Greenland ice sheet. So these polar glaciers are much bigger in size relatively. These are the largest ones. The one that I'm highlighting here in, does this work? Okay, so the one that I'm highlighting here in light blue, this is the largest glacier within the Randolph Glacier inventory, and this has an area of over 7,500 square kilometers. On the right here, I'm showing different types of glaciers. So these are mountain glaciers. The one at the top here is Siachen. This is the largest and the second longest outside of the polar regions. The main stem is over 76 kilometers in length. And then you can also see it has a very complex dendritic structure. And then we have some smaller glaciers. And then at the bottom here, I'm showing hundreds of really tiny glaciers. So there are over 200,000 glaciers globally, and most of them look like these. So they are less than 1 square kilometer. And when I'm saying that we are simulating these glaciers, we have to deal with all of these different types. They come in all shapes and sizes, and we want to be careful when we are representing these different categories. Okay, so with CISM, the Community Ice Sheet Model, we have introduced a new modeling framework to simulate these glaciers, their dynamics, their geometry changes, but also looking at related impacts. I do want to highlight that CESM is the first system model which has dynamic simulation of mountain glaciers. Now, CISM as a glacier model has representation of three-dimensional geometries. So as an example here, I'm showing what the input and output from CISM looks like. So this is distributed thickness, and this is on a 100-meter grid, and we can see a lot of details here. At the bottom here, this is the traditional flow line glacier model. So what it does is draw this flow line at the center of these glaciers and then compute all the fluxes and the properties at cross sections along these flow lines. So these are very different types of models. CISM is also a higher order dynamics. So there are a couple of different approximation of Stokes equations that we have within it. The one that we have been using is called DIVA, the depth integrated viscosity approximation, but recently Bill also did simulations with Blatter-Patine, and the results between these two are quite similar. Okay, so we have applied our model to the glaciers in the Alps region. And that is what I'm showing in the map here. So the blue ones are all the glaciers in these alpine mountains. There are around 3,900 individual glaciers, and again, they vary in size quite a bit. The largest one here is Aletsch, this trident-looking one. So this has an area of over 80 square kilometers, but most of them are around 10,000 square meters. So again, you can just get an idea of how different these glaciers are. And to make sure that we can represent all of these, we created a 100-meter CESM grid for our simulations. So I'm going to go show just one result slide. You probably have already seen this. So this is committed glacial mass loss. By committed, we mean that if the present-day climate continue for another couple of 100 years, what are these glaciers look like? Because ice mass take quite a bit of time to stabilize to their climate. So we started our simulation in 1984, and we are showing around 200 years. This is the state when the glaciers are going to come into equilibrium with the current climate, and you can see that it's actually more than 60% loss. I don't think it's 40%. Oh yeah, so around 2100, we're still going to lose quite a bit of mass. So the other thing I want to point out here is that you can see, what is happening here? Sorry. So you can see that a lot of these glaciers, as they retreat, they have started to split. So they have started to split, that you can see here as well. So many of these glaciers are now going to turn into smaller glaciers. The number of glaciers is going to increase. Of course, the net volume is going to decrease. And this has significance because these smaller glaciers are more prone to geohazards. The bigger ones, they're more stable, they're more rooted, but once we get into these tiny glaciers, we are getting into a domain where the propensity for geohazards is going to increase, and this is a point I'm going to come back to later as well. Okay, so if you're interested in more detail about all the things that we have done, how we are calibrating and validating, we have our manuscript under review in GMT. So the preprint is available, and you can also see the review process. One thing that one important activity that we participated in was Glacier Map 3. And the main question that this phase of the Glacier Map was asking is what would be the equilibrium state of all of these glaciers if the temperatures were to stabilize at different levels. So I've already talked about the present day levels, but also if we have increment as compared to pre-industrial temperature levels. And this is one example of the result from that paper. So what it's showing here is the committed loss of global glacier mass at different temperature levels as compared to pre-industrial. So we are going to lose half of the global glacier mass at 1.6 degree warming. At 2.7 degree warming, we are going to lose 75% of these. But again, these are global. Regionally, glaciers have different sensitivities. For example, for Alps, we only need to go to 0.9 degree to lose half of the mass. And you have already seen before that we are way across that threshold. So we are somewhere around 1.2 right now. So the glaciers in the Alps are going to lose a big chunk. If you're interested in more details for different regions, this paper is out as well in Science, so you can take a look at all the different regions and different models, what they're showing. Okay, so that was a very quick introduction of the capabilities that we have within CESM. So I'm going to talk about one ongoing model development. And this has to do with the mass balance scheme. When we were doing our simulations, we found that, of course, the glaciers are most sensitive to our mass balance parameters. So this is the most important part of looking at glacial changes. Presently, what we have is a rather simple scheme called a simple temperature index scheme. CESM is internally computing this mass balance based on this two input forcing, temperature and solid precipitation. So we get the mass balance at each grid cell based on temperature and precipitation. And we have two parameters that we are tuning for each glacier, but the most important one is this mu, which is temperature sensitivity parameter. It is also known as degree day factor. So we have some input target mass balance that is coming from an external data set, and we try to reach this target mass balance. One thing you can see here is that first, mu is glacier-wide, so we have a single temperature sensitivity parameter across the span of a glacier. And again, this input data set is also glacier-wide, so we have a single mass balance value across the span of the glacier. In reality, these glaciers are not so homogeneous in their length or in their span, so the terrain effects are really important. And here I'm showing a figure of aspect. This is for LH Glacier, so I've just shifted a little bit so you can see some regions here which are in the shade. So these are north facing, or northeast, northwest facing slopes. Then you can see some other regions here which are south facing, and we know that north and south facing slopes receive different radiation and they have very different energy balance. So this is one thing that we need to consider. Another is elevation change across the span of the glacier. So here I'm showing the 10 largest glacier in the Karakoram region. And if you just look at Batura up here, its snout, this dark pink color, is at an elevation of around 3,000 meters. The upper tributaries are at elevation of over 7,000 meters. So within a small span of this glacier, we have an elevation difference of over 4,000 meters. So we know that a single mu parameter is not very helpful for these types of simulations. So to address this, we are looking at a different component of CESM, which is the Community Terrestrial Systems Model. Specifically, it has a configuration called hill slope hydrology. And this hill slope hydrology can account for this aspect and elevation classes. So what we do is we use high resolution DEM to classify a grid cell or a polygon or a watershed into smaller hill slope classifications. So these are user defined. What we did here was, this is in this river basin, we picked up one watershed. We used DM to simplify the topography at subgrid level. So here I'm showing 16 hill slope classifications, 4 for aspect and 4 for elevation classes. And this is what we use to downscale all the information. I'm not going to go into the details and the equations how we do that. So this is just one example where we have snow coming from the atmospheric forcing. In this case, this is ERA 5, which is ½ degree. So we have one value across this domain, but we can use the hill slope to downscale all the information, and this is the type of details that we are going to get. So if the HPC hadn't gone down last week, I would have some more definitive results, but you would have to use your imagination a little bit. This basin that I'm showing here is the one that I'm highlighting here in light blue. So let's just pick another one, for example, Baltoro. So the watershed that Baltoro Glacier is located in, we are going to do the same thing. We are going to downscale all that information, snow, precipitation, all the energy budget variables. And then we are going to compute the mass balance, and we are going to feed that to CESM. Of course, I'm making it sound a little more simple than it really is. It's going to take us another year or so to fully implement this. I think I've been saying this for at least 2 years now that we're going to do this, but hopefully by next CESM meeting, we should have this, this development. So this is one of the major elements that we are working on right now. Okay, so I'm going to wrap up with a couple of research applications that we are pursuing. The first one is, of course, related to water resources and hydrology. In mountainous regions, glaciers are a very important freshwater resource. So there are a couple of different domains that we are looking at, but it's a combination of CTSM, hill slope hydrology, and CISM to look at cryosphere hydrology assessments. In this figure here, I'm showing some glaciers in the Rocky Mountain region. So this is Wind River Range. And we have smaller watersheds. So these are both snow-dominated and glacier-fed watersheds. And these are the type of assessments that we can do that, for example, we can look into partitioning between glacier melt, snow melt, and base flows in these rivers, in these watersheds. So I've just set up a domain for US, but we are also doing similar assessments for the Himalaya Karakoram watersheds. But the application that I'm most excited about is related to geohazards, and I alluded to this earlier as well. And we know that these glaciers are very important in how they alter or how they create the terrain surrounding them. They affect glacial lake formation, they affect permafrost, they affect drainage patterns. So you can just think of anything, and glaciers play a role there. And with all of these, glaciers are linked to geohazards. And you would have seen in the news recently of this glacial collapse in Switzerland. So this was the Birch Glacier. It just collapsed last week. And this glacier was located here. So it was a very small one. It was, I think it had an area of only a half square kilometer. But its effect, the impact was massive. So the entire village was destroyed. So we wanted to see, of course, we have this three-dimensional higher order model now. Can we use that to look into geohazards? So for that, what I did was take CESM simulations, and see how that affects topography change. So we're looking into the future now. We started our simulations in 1984. So we have, it's the same figure that I was showing earlier. The star here is showing where we are standing right now. So we're looking upstream, and this is a 3D view of LH Glacier. And you can see the peripheries here where we are in 1984. So let's look at 2021 and 2084. So just within 100 years, we lose a big chunk of glacial thickness here. What that does is expose a lot of this slope that you can see in this region. So there are a couple of things happening here. Of course, the first thing is that we are getting an exposure of this side valley walls that would release more sediments, more rains, and that could result in more landslides and rockfall activity. But another thing happening here, which you cannot see in these still images, is the subsidence, especially along these steeper slopes, because there are glaciers located in these slopes as well. So as they are thinning, these slopes are subsiding. And that results in weakening of the valley walls and the slope, and of course, we can get slope instability and failure. So this is an area that I'm exploring right now. And I think it's a new area because usually when we think of Earth system model, we don't really bring in this solid Earth component, these geotechnical components. So what I want to explore is how we can bring together ice dynamics modeling with slope stability analysis to look at these geohazards. And of course, we want to look into the future. So I have a couple of ideas here, but if there's anybody who is a geotech expert, the model, the slope stability model that I've used in the past is rock science slide, but maybe there are better ones out there, so I'm open to discussions on this topic. So with this, I conclude my presentation, and I'm happy to answer any questions.
Questions?
Thank you for the talk, very nice. One question about your sort of classification of elevation, like the map that you use. It is something that you give as an input, right? That you know, yeah, because I think I didn't understand that very well. So it's something that can evolve while you run a simulation if you're changing the geometry of the glacier?
So this map has nothing to do with CESM simulation. I was only showing it to give a sense of the difference in elevation across the length. What we give to CESM is the surface topography. Surface topography in the rest of the terrain does not evolve. Only the glacier thickness changes. So we can now translate that glacier thickness change to a surface topography change using some other, I was using geospatial analysis. But CESM is not going to give that information.
Thanks. Yeah.
I'm just curious how you verify your glacier model. So you're showing projections into the future, but do you also use the model to simulate recently observed historical change to verify?
Yeah, so we did do some validation. The thing is that for these glaciers, we don't have a lot of observational data sets. We have to, because we are doing this distributed modeling, we rely on distributed observational data sets, mostly satellite derived. So there were a couple of data sets on mass balance for specific regions and on surface velocities. And that is what we used to validate our output. And that was all historical. So we identify historically if we are close to those external or independent observations of velocities or mass balance, and then we use it for future simulations. The other thing in our case was participating in Glacier MIP, and that was another an indirect way of validating our model because we were participating with traditional glacier models to see where we are in the span of all of their whatever output they're giving. So this was another way to validate our model output. But yes, we do as good of a validation as we can for these glaciers.
Thank you again. Thank you to our speakers. And thank you for sticking around as we are running a little bit late. So thank you and enjoy the rest of the day. Thanks.